Okay, thank you very much for the invitation and for putting together this very nice conference. And I shall begin by disagreeing with Rodrigo that this interaction between his group and me and my group didn't start when Rodrigo first invited me here. That started long time ago when we were both drunk at the end of a conference, I think in Porto Alegre. Was it Florianopolis? I can't quite remember that. But I mean, I kind of challenged Rodrigo to, I mean, you should start looking at C-star algebras. And eventually that evolved into this nice interaction that we've been having. So thanks very much for that. So my topic is KMS states and row algebras. And this is a joint work with Bruno Braga. From IMPA. And that's also an interesting interaction. I thought I knew all of the operator algebraists in Brazil. I mean, most of them are either my former students or my great friends. But suddenly I heard about this new arrival in Brazil from a PhD in North America, and whom I've never heard about. So I invited Bruno to Florianopolis, and I eventually found out that he started out a career in functional analysis and Banach spaces, and then eventually he got a postdoc in Toronto with Elias Farah, where he veered into C-star algebras. So this is when we started working together. So the central object in this business is coarse spaces. So let me give you a definition. A metric space X, say with a metric D, is coarse, or also uniformly locally finite if for every R bigger than 0, the number of points in the ball of X, the ball centered at X in radius R, is finite. The balls are finite. And they're not only finite, but they're uniformly finite in the sense that supremum for all points is bounded by the same number. Okay? So first time I heard this definition, I held myself from laughing. Because, I mean, of course, that implies that the topology on X is discrete. Okay? So I thought, hey, what's this guy saying? I mean, I know everything there is to know about discrete spaces, but you see that the story is not quite that simple. So examples, of course, in most of the examples, X is a countable set. And the examples are, of course, the natural numbers with the metric induced from the real line. The integers, if G is a finitely generated group, then we can define a norm which is the smallest, the infimum of the numbers such that G can be written as a product So you fix a generating set, and every group element can be written as a product of the generators. Right? The product of generators is a word involving generators, inverses of generators. So you write it out as a product of either generators or inverses of generators. You count the number of elements in here, and you minimize that number. So you can define a sort of a modulus of G, and then you define the distance of G and H to be the modulus of G inverse H. So that is an important example. In the category of coarse spaces, morphisms is another definition. A morphism of coarse spaces is a function such that, what would you say, such that f is continuous. That seems to be a stupid notion because it doesn't say anything, right? So the condition is that for every r bigger than 0, the distance of f of x to f of y is bounded, the supremum for all x and y in X, such that the distance of x and y is less than r. This should define it. Okay. So it's a sort of a Lipschitz condition that bounds the distance of x to f of y based on the distance of x and y. And so these are the morphisms that people usually deal with. So once you have a category, you can speak about isomorphisms. And this is where people who have been laughing should stop laughing. You want to characterize the spaces up to isomorphism, for instance. So let me give a loose definition, because there are many versions of isomorphisms. Let's say x and y are the same. So this is my loose notion of isomorphism. So let me just, as a joke, introduce, I'm going to give you 3 versions of isomorphisms. The first version should be if there exists a bijective in isometric. It's a very strong notion, and I made up that definition just for perspective. The other notion is if there exists f of x and y bijective coarse. Did I say this? So a morphism between coarse spaces is also called a coarse map. Okay. If there is a bijective morphism with F inverse also coarse. So here's a second definition. So would you say that those 2 spaces are isomorphic? Certainly not under 1, but are they isomorphic under 2? So we know how to map the natural numbers to the integers, right? 0 goes to 1, 1 goes to -1, you go like this, right? So by doing this, you have nearby points which start going further and further apart. So that first idea of a map between here and here, that's definitely not coarse. Okay. So we'll see that they are not. So the third definition I want to show you. Yes, yes. 1 is certainly stronger than 2. So this is not a list of conditions. This is a list of options. No. These are 2 different options, right? So I'm going to give you 3 options, and you choose the one you like the most, right? So obviously, 1 implies 2, right? They're not equivalent. They're not equivalent. There's simply alternatives for a definition of what your idea of isomorphism should be. Okay, and the third one, which is quite important as well, if there are maps from X to Y and map from Y to X, coarse, such that F and G are F composed with G or G composed with F is not quite the identity, but G of F of X, the distance between G of X to X is controlled in the sense that the supremum for X in X, this is finite. And same for the other direction of composition, Y in Y, the distance of F of G of Y to Y is finite. Okay, so this is a third definition, which is certainly weaker than 2, right? So 1 implies 2 and implies 3. So you may, of course, depending on what properties of the core space you are interested in, you might like to choose one out of the 3 conditions here. So, for instance, there are results such as, suppose you know that Zn, suppose that n and m are 2 integer numbers such that Zn, the grid, is isomorphic to Zm according to one of the 3 conditions there. Say according to the weakest one. Could that happen? I mean, when is Rn isomorphic to Rn as vector spaces? We know that that only happens when n is equal to m, and this is, again, the case here. So, I mean, once you have this category in mind, then you realize that it's not that simple, right? The reason you laugh when you hear the definition for the first time is that you think that they're all the same, thinking about isomorphism being homeomorphism, but we're not talking about homeomorphism. The whole idea is that this category of core spaces tries to capture the large-scale geometry of X, not the local geometry, right? So questions you might want to ask is, suppose you take a ball, you fix a point, you take balls of increasing radii. So how does the number of points in this ball, how does it increase? Does it increase polynomially, or does it increase exponentially? So those are questions that you might want to ask. Okay, so now to C-star algebras. So what I want to do, I want to give you the definition of the uniform row C-star algebra of a given X. X, of course, is going to be a fixed metric space, a fixed metric space which is coarse. and that will be denoted by C star U of X. So what you do, you first define a translation, or I should say a partial translation, is a triple A, B, F, where A and B are subsets of your space X. F is a map from A to B. It's bijective. And the crucial condition is that the distance from X to F of X should be small, should be controlled in the sense that the supremum from X in A, this should be finite. Okay, so a point moves away from its origin by a fixed amount. This, by the triangle inequality, this immediately implies that F is coarse, right? Converse is definitely not true. So why is that called a partial translation? For example, if X is a finitely generated group, remember the distance of G and H is the absolute value of G inverse H, then left translations say lambda A, lambda G defined by GH, this is a translation, right? Because if you multiply, maybe I should say lambda X of G is equal to X G. If you multiply both G and H by X on the left, the X cancels here, so the distances here is a fixed number, right? So this idea tries to capture the translation in the group. In fact, this example of course spaces is one of the most important ones, and some of the terminology is based on the group case. Okay. So for instance, this for you to gauge your understanding. What are the translations when X is this coarse space? So X is a subset of the real line, and you got 0, 1, square of 2 is 4, square of 3 is 9, square of 4 is 16, and so on. Okay? So what would be a partial translation on that space? Well, every point has to move not too far away, right? So if you are here at 9 and you want to move, if you want to move a short distance, you better come this way because 16 is much further away, right? If you are out there at 1,000 square, you have to go to 1,001 square or 999 square, which is quite far away. So what's the result? So here, every translation is equal to the identity except on a finite set. Right? So that's a very important, this is an elementary example, but it's very important for for counter examples and stuff like that. Every partial translation as well, yeah. Yeah, no, I didn't. It's just partially defined. So you have to choose a set A for the domain, and if that set is finite, then you're in business. Any function is a partial translation. If that set is infinite, then if you're far away, you won't be able to move much. Okay? I like this example because it gives a nice idea. Any further questions? I like questions. I love questions. I mean, among other things, questions tell me that I'm not talking to myself, which often happens when you're giving a talk, especially if you're not a very good speaker like I am. So, okay. Now, one observation, which is notice that the set S of X, the set of all partial translations, is an inverse semigroup under composition, right? The trouble is that composing partial maps is slightly tricky. If you have a partial map from A to B, and you have another partial map from A prime to B prime, then how can you compose those maps? Because if you start here and go through F, then you may not be able to follow up with G. So you look at the intersection here, pull it back under F, and the composition is only defined here, and that goes to here, and then eventually goes to a piece in here. So that map from here to here is the composition of F and G, right? And using this partially defined composition as the group operation, the set of all partial translation is a semigroup, right, under this partial composition, and it's an inverse semigroup. I'm not giving you the definition of an inverse semigroup, but it's a special kind of semigroups. And so the definition, which is a propaganda of my area. This is totally inappropriate from the historical point of view, but I just found this opportunity to publicize some of my ideas. The row algebra is the reduced C-star algebra of the tight groupoids of the inverse semigroup S of X. So I mean, if John Rowe was here, he would quickly jump on my neck and strangle me because this is. But sorry about that. Let me give you the correct, the historical definition. So you look at L2 of X. Just look at X as a set, it's an index set. Look at L2 of X, and for every partial translation, F from A to B, define an operator VF from L2 of x to itself. No, I said just look at x as a set, as an index set. Okay. L2 of x is just simply square summable sequences indexed on x. Complex numbers. It's just a sequence of complex numbers, right? So, I mean, when you talk about L2 of the natural numbers, you don't care about any structure. Yeah.
But you have a norm and you know what the number is absolute value.
Yes, of course. But so L2 of x consists of sequences where each AX is a complex number. Yeah. So the absolute. Okay. All right. It's just a question of a proper. I mean, half of the debates we have in life are actually about the proper definitions. Once everybody agrees on the definitions, everything is clear, right? So I'm sorry I didn't. Yes, of course. Okay, so we view L2 of x as a Hilbert space. This is if x is countable. This is the standard separable infinite dimensional Hilbert space. So I'm going to define certain operators on L2 of x, and the operators are given by this L2 of x here, I'm going to call delta x the standard orthonormal basis, right? And I'm giving you the definition of this operator only on the basis to begin with. So Vf of each delta x, I map that to delta f of x if x is in the domain of A, right? And if x is not in the domain of A, I simply throw the towel and I say 0. Okay. And it's easy to show that this map, which has only been defined on a basis, extends linearly and continuously to the whole space and gives what's called a partial isometry on your Hilbert space. And then we define C star U of x as an algebra of operators as an algebra of bounded operators on the Hilbert space L2 of x is generated by the set of all Vf, where F is a partial translation. Okay, so we have a bunch of operators. We simply generate a C-star algebra out of that. So in order to familiarize ourselves with this gadget, I see that I am in deep trouble in terms of time, so I'm going to require those 3 minutes back with a huge interest. But, no, sorry, that was just an empty threat. So in order to have an idea of what this algebra looks like, notice that if A is contained in X, then the identity on A is a partial translation. Right? Because nothing moves, so it's a partial translation. And the V, the corresponding operator, V identity of A, what is it? It's orthogonal projection onto L2 of A. So this is a projection. This is not only a projection, this is a diagonal operator, right, regarding the standard basis. And if instead of taking all of the VFs, you only take those, what is the span of those guys? Do you have a guess? What is the span of the V's that you get if you restrict yourself to those F's? So every operator, every diagonal operator which has zeros and ones only, right? Every such operator occurs in here. It's every bounded diagonal operator. Right? All bounded diagonal operators can be written like this. So as a C-star algebra, what's that isomorphic to? This is L infinity of X. Right? Every sequence, every bounded sequence indexed on X placed down the diagonal gives you a bounded operator, and you get that here. So, this is contained in the row algebra. So the row algebra is non-separable. That's a bit of a problem, but okay. So another example of operators, say X, A is a point, and B is another point, and F from A to B is the only possible map, right? If you look at what is VF? So VF is one of the operators that people call standard matrix units, right? That's sometimes called EYX. So that's the operator that acts on a single vector, kills all of the other vectors, acts on a single vector, and takes that somewhere else. So what's the span of the VFs of this form? I can see here that I made a mistake. I intended to write the closed linear span, right? Sorry about that. And again here, so the answer is correct, that this is just a finite matrices. And what is that? So I'm saying my game is here. The row algebra is defined by the span.
Oh, that takes 2 points. 1 point is 1.
Yes. Okay. Yeah. The Fs are the ones in example 2. Only compact operators, right? If I were talking about the weak topology, then that would be, yeah. So this is K of L2 of X, which I'm going to describe, call it only K. So one result that, very impressive result that Bruno was involved with, and this is by Baudier, Braga, Bruno Braga, Ilias Farah, Kukro, Vignati, and Willett, states that if C star U of X is isomorphic to C star U of Y, then X is isomorphic to Y under condition 3. That's a rigidity result, which is it's been open for quite a while, and this is a recent Invenciones paper. Certainly that's why IMPA decided to hire Bruno.
One is sort of credible. Three
I mean, one is false. No, it's loser. The stricter one is 1, right? The less strict one, but definitely 1 is it's false, right? 1 is definitely false. But okay, so I know that my time is short, but this is essentially where the talk should start. So what I'm going to do is I'm going to introduce a flow meaning a 1-parameter group of isomorphisms on C star U of X and study the KMS states. Okay, so this is how we do it. So fix any function h from x, of course, fix a space x, of course, I'm fixing a coarse space x, and fix any function to the real line, bounded, unbounded, whatever you want, and consider and let H be the diagonal matrix with H of x as the x entry, right? Diagonal matrices have zeros outside the diagonal. The diagonal entries are labeled XX. Just plug in H of x there. So this gives you a diagonal matrix, and every matrix gives you an operator. Also, let H, and by abuse of language, H for me is the function. Same letter denotes the diagonal matrix, and by the same letter, I'm going to denote the operator defined by this matrix, the possibly unbounded self-adjoint operator on L2 of x. Okay. So we know that self-adjoint operators give rise to 1-parameter group of unitaries. So if I write UT equals to EITH, this is a unitary. This is a unitary operator, and collectively they form a unitary group. And so I can define sigma sub t as a map from B of H. Maybe I'm going to start calling L2 of x simply by H from now on, okay? So the map from B of H to B of H given by sigma t of some operator A U I T H A U minus I T H. So this is a 1-parameter group of isomorphisms, of star automorphisms. By Stone's theorem, we know that all such gadgets are of this form for an appropriate self-adjoint operator. Yes, U should be E. Sorry. I should either write UT or the full notation. Okay. And it's not hard to see that sigma t of the uniform row algebra, which is a subset here, is equal to. So we can restrict this one parameter group to the subalgebra and get a flow, right? There's a slight technical problem. Has anyone spotted it? I mean, if we deal with one parameter group of automorphisms of von Neumann algebras, we are usually interested in the weak topology. And this is defined as a C-star algebra. So we should talk about the norm topology. And groups on C-star algebras are usually required to be strongly continuous with respect to the norm topology. So the question is that this might not be strongly continuous. So we need some condition on the function h to make it strongly continuous. And the proposition, which is quite easy to prove, is that if h is coarse, then sigma is strongly continuous on C star u of x. If you don't know what's a strongly continuous action, the definition is here, i.e., for every A in the algebra, the map sending the real number t to sigma t of A in the algebra is continuous with the real line topology here and the norm topology there. I mean, you can always talk about the set of operators which are continuous with respect to the set of all elements A such that this is continuous forms the C-star algebra. It's not easy. I don't think it's easy in general. I think it's got to do with the position of the algebra relative to the spectrum of the operator H. There's some difficult questions there. Okay, so this is the flow. And so from now on, we fix X and H. And I want to discuss the KMS states relative to this flow. Do I need to define KMS states? Boss? Yeah? Okay. So you owe me another 2 minutes for that. Okay, so the definition is KMS state is a positive linear functional phi on our algebra. So I mean, in general, say this is an algebra A, an abstract C-star algebra A with an abstract one-parameter group. You can replace that by A. Positive linear function from here to the complex numbers. By that, I mean that phi of A star A is positive for every A, such that, and for some reason, the KMS condition hasn't entered my mind yet. And I often mix the order of things, but I think it is phi of A sigma I beta of B is equal to phi of BA. If you spot a mismatch in order here, please let me know. let me say, a KMS state at the parameter beta, which is a real number, often called the inverse temperature, such that this is the case for every A in the algebra and every B in the algebra. So every, let me shorten this, for every A and B with B analytic. Okay, an analytic element, you notice that B is a real parameter. So if that was a real number down here, everybody would understand, but I'm placing a complex number here, so that's weird. So the point is that the function sending T in R to sigma T of B in the algebra may or may not admit an analytic extension to the whole plane, right? If it does, then I get a function by abuse of language denoted by this. And so if B is analytic, then I'm allowed to plug in any complex number here. So I plug in I beta. So this is a condition that has a long story, and it was introduced by Kubo, Martin, and Schwinger after they realized that the standard Gibbs states satisfy this condition and are actually characterized by this condition. Yes, I should have been more precise here in giving the definition. I want to normify it as one. Yeah. So those two conditions define what's called the state on a C-star algebra, right? It's a linear functional which is positive and has norm 1. It's a consequence. If the algebra is unital, those two conditions imply that phi sends 1 to 1. And if you require that phi sends 1 to 1, then that implies that it has norm 1. So it's a big interplay between algebraic and analytic conditions here because of positivity. Positivity is a very strong condition. Okay, so I should say that, as you can see, whether or not phi is a KMS state depends on a value of a chosen parameter beta, which the physicists call the inverse temperature, right? And so let me, my time is not yet over, so let me head straight towards the main result, and then in the remaining time, I may try to add some more information on that. So the main game in here is the study of KMS states as they vary with the parameter beta, right? So if this is the real line here, you have your beta, and you can try to find what are the KMS states for this value of beta, right? So you may, or there may be one, there may be none, and there may be many, right? Often it happens that there is there exists a single KMS state, and as you move beta, suddenly you reach a critical value in which there's more than one, right? And then you may move on, and then suddenly there's none anymore, and then there are lots. And when this happens, people say that a phase transition occurs at this temperature, And I mean, there are models in which this phase transition here represents phase transition in the usual sense, in the usual physical sense of the word. Like when you boil water, water has under 100 degrees Celsius, under 100 degrees Celsius means beta larger, because beta is the inverse of the temperature. Under 100 degrees Celsius, water is, say, let's ignore ice, but close to 100 degrees and under, water is liquid. Then exactly at 100 degrees, there are two states which coexist. Water is both liquid and vapor at 100 degrees. And then if you if you heat that up further, then you only have a single state, which is vapor, right? Then maybe further on, you would find other states. And the same thing happens with a magnet. If you heat a magnet, after a certain critical temperature, the magnetization disappears, right? And that can be understood from the point of view of KMS states and this play with beta. So in order to head straight to the main result, let me state it right here. So let X be the n-ary tree. That's an important example of a core space. The n-ary tree has a root, n branches, and out of each branch you have further n branches. And then out of here you get another 3, and so on. So the space is the set of all vertices in the tree. Okay? What's the distance? Well, the distance is the path distance. If you want to know what the distance from this point to this point, then the distance is the shortest path that leads from this point to this point, which is in this case is 1, 2, 3. Okay? With path distance. And let h of each point x be the length of x. Every point in x can be written as a word. This is the empty word. And then according to which branch you follow, you add a word. So if you look at the alphabet of points 1 to n, then x is simply the full language on the alphabet A. All sorts of finite words in letters from this alphabet. And so you can talk about the length of a word, right? So that gives you a real valued function. Then the KMS states are as follows. This is the line for betas. There's a critical temperature at log of n. Okay. Below log of n, there are no KMS states. Above log of n, there are unique KMS states, which happen to be which happen to extend to the whole B of H These are actually the Gibbs states, which are defined on the whole B of H. And so the only question is what happens at log of n. So in this case, there are many. In this case, for beta equal log of n, there are, now I should say that if there are two KMS states, then automatically there are infinitely many, because the convex combination of two KMS states is always a KMS state. So if there are two, there are infinitely many. So people are not really so much worried about the number of KMS states, but the number of KMS states which are extreme points. Beta is a parameter. Yeah, I mean, once the algebra and the flow is fixed, then you play with the parameter. For different values of the parameter, you may or may not have KMS states. So we are playing with the parameter here.
It's easy to see in your general framework that you cannot have a state that is KMS for two different distances.
The same state, yes, it's very unusual, but it can happen. It can happen. It's very non-physical. In fact, the example of the squares of natural numbers, there are states which are KMS states for every temperature. So it's a weird example. It's a weird example. Yeah, yeah. It's I can show it afterwards to you. I mean, it still kind of gives a short circuit in my brain, but it's pathological. Yeah. Okay, so I was talking about the extreme. So the set of all KMS states is the set of all KMS states is called K beta. The set of all KMS states at a given temperature. This is a compact convex set in the dual of the algebra. Right? It's a linear function that lies in the dual. So this is in fact inside of the unit ball. So by Alaoglu's theorem, the unit ball is compact, and this is a closed set, and so this is a compact set of states. And so we know by Krein-Milman's theorem that every compact state is the convex hull of the extreme points, right? So the crucial thing is how many extreme points are there in order to tell you how big this space is. Yes, yes. And there are examples. Choquet simplices can be very weird. There's this Bauer Choquet simplices, and I'm interested in studying that here. And I think the extreme points are closed in this case, so which is the nicest kind of Choquet simplices. So, as I say, phase transition does occur in that, and that's at this temperature. So there's more than one at this temperature, right? How many? How many? So if I say Aleph naught, would that impress you? There's a bunch of KMS states. If I say 2 to the Aleph naught, then that should impress you even more, right? But the actual answer is 2 to the Aleph naught. So it's this outrageous amount of KMS states there. Okay. So this is the minimal stopping point that I could possibly envision, and I guess I am already over time, so I'll be glad to answer questions and give you more details. You know, of course, My point in preparing this lecture is, I mean, if you're a specialist, if you're interested, go look at the paper, right? So I strived to give an elementary talk, and of course, you pay the price for not being able to go too far. But thank you very much.
So you have some kind of geometric characterization for this amount of extremal points? Because in graph algebras, you have sometimes with the infinite meters. In the Thiago paper, you know, we have to look for the graph, and here you have to say something. Why you have so much people?
Yeah. So the point here is that as it often happens when you're dealing with KMS states, we know that the row algebra contains a copy of L infinity of X, right? As I showed you at the beginning. And it's easy to see that there is a conditional expectation from here to here, which is simply take your operator, view as a matrix, and erase all of the non-diagonal entries of the operator. You get a diagonal operator, which is the fourth element in L infinity. And it's a theorem that every KMS state here necessarily factors through this conditional expectation. That's something that I guess Marcelo is not impressed by that. So actually what you have to do is called the factorization psi here. Actually what you have to do is study those states, right?
They have to be KMS.
No, they have to satisfy some condition in order for this to be KMS, right? And the condition is an easy condition to be described here. But what I would like to point out is that this is a commutative C-star algebra. Therefore, it is the continuous function. Continuous is a set of all contingent functions on some space. Which space is that? This is called this beta is not the inverse temperature anymore. This is just the usual notation for the Stone-Check compactification of X, right? And the Stone-Check compactification of X consists of all ultrafilters on X, right? So nobody knows a single example of an ultrafilter except for the most basic ones, which corresponds to which are the principal filters, right? So the points in the space they simply don't exist unless you assume the axiom of choice. So that's a very hard space to deal with. Now, linear functions in here are measures of the space. So what we're actually dealing with is measures on this weird space. So this is a big hurdle in order to be able to describe a KMS state. So all of the results are pretty much indirect, and I would love to be able to give one example of a KMS state at this temperature. And I really think that's not feasible, but maybe some people can work out the details.
Another question, maybe?
I think I can speak about that. I'm sorry because I'm ignorant about this row algebra.
Oh, you're very ignorant, especially about KMS states.
From what you said, what's around here doesn't matter. It's what's outside that matters. It's the far. So I kept hoping that you would take the quotient by the compact.
Of course, of course.
So are these? Am I right that the KMS state log n happen in that quotient?
Exactly.
And is it true that then the KMS state condition disappears and you just have all measures?
No.
You still have some condition.
You still have some condition.
But not too much because you have so many.
The quotient of the row algebra by the compacts is called the row corona, right? And it's a version of the Kunz-Krieger algebra versus the Toeplitz-Kunz-Krieger algebra. And everything takes place on the row corona, right? So this says that the tiny bit of the space that you can actually understand is swept away, and you have to only look at the place that you don't understand anything. Right? And there, this algebra has a center. The quotient has a center. And the center is called the Higson corona. The Higson corona is the corona of a compactification of X, very specific compactification. So this algebra has a center. Whenever an algebra has a center, say if A is a C-star algebra with a flow and phi is a KMS state on A, and if you have an element Z belonging to the center of A, then phi of ZA divided by phi of Z, say Z is a positive element in the center, such that phi of Z is non-zero, then this new linear functional on A is a KMS state as well. So the center decomposes the KMS states. We can show that every extreme KMS state is actually supported on a single point on the center, right? So the proof of this result consists of this plus the fact that the size of the spectrum of the center is this big, and plus the fact that there exists one KMS state whose corresponding measure has full support on the center, and which in turn implies that there is a KMS state supported at every point. So that's the proof. But it's not true that not all states on the Kunz algebra are KMS states, right?
There is not restricted all points.
There, I don't know. I'd love to understand that. I mean, we know. So the center of the rho corona is called Q U of X. There's a C star U of X modulo the compacts. So the center of this is the continuous functions on the Higson compactification, right? So we know that every extreme KMS state here is such that, so extreme KMS is such that phi of A is equal to A of X for every A in the center, and some X. Right? We know that for every KMS state, when you restrict it to the center, is a character. Right? So this is the point where the state is supported in. Right? Of course, there's only one X that can play a role in here. Now, this actually defines an ideal in here. You can look at the quotient by this ideal. So it may be that all states satisfying this condition are KMS, maybe. But we know that there exists at least one. But from this, in working with this, I have sometimes I have a feeling that in fact there are many states on this condition, but I can't even prove that there is more than one state supported on X.
Okay, people, since we are advancing the time, maybe you will ask for during the coffee break, otherwise people will kill me. So sorry, so let's take the speaker again.
Thank you very much.
a little modification, not so little actually, is a big modification. We just shift up the speakers, and the reason is that Klaus Thomsen is not here. To be honest, he was one of the first persons that accepted to participate of this conference a long time ago, but after a lot of time happened, and he was not able to speak today. So the next speaker is Johannes Christensen from KU Leuven, and he will speak about the KMS spectra for group actions on compact space.
Thank you very much. You can all hear me, I suppose? Perfect. So first of all, thank you very much for the invitation to come and speak at this conference. It's a great pleasure to be here. It's my first time in Brazil. I spent the last couple of weeks traveling around and seeing this very beautiful country. It is my first time in Brazil. It was not supposed to be my first time in Brazil. I was also invited to speak at a conference in Florianópolis in 2018, which was the same year where exactly the same time I had to hand in my PhD thesis. So being the student I was writing up my PhD thesis like the last couple of months. It was very, very intense. So I didn't have a lot of time to like plan my trip to go to Florianópolis. So I submitted like an abstract. I bought a ticket, I bought a hotel, it was all good. Except for the fact that a few days before leaving, I realized that I forgot completely about vaccinations. I had not gotten ever a yellow fever vaccination, and apparently there was like an outbreak. Knowing nothing at all, I was too scared to go, because apparently you can die from yellow fever. So I ended up not going. So this shouldn't be my first time in Brazil, it is. I'm sad that I was not there in 2018. The point of the story, of course, is that I have a very bad memory. I should have remembered my vaccine. If I forget anything else throughout the talk, you should please feel welcome to just ask me. Well, I think ignorance is a bliss, right? I looked at the map and I was scared to go. So, but yeah, luckily this time I got it. It should all be good. If I forget anything else, please ask me. I will try to remember it.
You're making it worse. Now you really regret.
Yeah. It's good that I can be here now, at least. And of course, it's a shame that Klaus could not be here, but Klaus Thomsen is actually somehow present in this talk as well, because it builds on work that I did together with him. So his name will appear, and hopefully he will somehow be here in spirit, in that sense. So what I really want to talk about today is somehow a connection between quantum statistical mechanics, KMS states on C-star algebras, and dynamical systems and ergodic theory. And this is somehow the whole point of the talk is this paper I wrote with Stefan Vaz on the subject, but somehow the first paper on this problem was a paper between me and Klaus. So in spirit, I really do think he's here. So this connection between quantum statistical mechanics and dynamical systems really goes over like a very classical connection in the world of C-star algebras, which is one between dynamical systems and C-star algebras. So since I was not really sure how strong a background in this kind of thing people had, I figured I would start the talk out with a slow warm-up, introducing a little notation that we will need throughout. So first, let me say something about group actions and cross-product C-star algebras. And then I will talk about KMS states and one-parameter groups. And then I will talk about something called conformal measures. And in the end, I will briefly go through my results with Stefan on these things. So first of all, what do I mean by group actions and cross products? Well, throughout this talk, the groups I will talk about will be discrete countable groups. So this will always be the group that I'm thinking about. The unit will always be denoted by E, and the topological spaces I will talk about will be compact metric spaces. So what is a group action on such a space? Well, it's just a family of homeomorphisms indexed by the group, satisfying that the homeomorphism corresponding to the unit is the identity, and satisfying that when you compose phi g with phi h, you should get phi g h. So basically these homeomorphisms respect the group structure. And normally when writing these things, you will just write g acting on s like this. For this, it will mean that it acts by homeomorphisms, and you will write g dot x for the action of the homeomorphism g on the point x of the space. So what would a standard example of this be? Well, you can have the nice discrete countable group, the integers. If you take a compact metric space X and consider any homeomorphism on the space, you can actually define an action of the integers by just setting your homomorphism phi n to be phi composed with itself n times. Makes sense for minus, say 3, because you have an inverse, right? And it turns out that this will actually define you a group acting of the integers if you just set down and check these things. The point being that specifically for the integers, the group actions are in bijective correspondence with the homomorphism on X. If you have more complicated groups, of course, there's more relations that these things have to satisfy, and the picture becomes a little less clear, but basically you just have this kind of group of homomorphisms, right? Okay, so I'll need a little terminology on this kind of group actions on the dynamical side. So as always, these will be a countable discrete group. X will be a compact metric space, and G will act on X. A relevant notion is that of an isotropic group. So this is something we purely talk about in dynamical systems. So whenever you have a point of your space, you can consider the subgroup of the group of the elements that act trivially on that point. That will be the isotropic group at the point. We'll also need to talk about minimality. So we say in this setup that the action is minimal when each orbit is dense. So you take one point of your space and you act by the group on it, and you want some dense subspace of your compact metric space. Then we call it minimal. And lastly, we'll need the notion of topological freeness. Topological freeness basically means that these isotropic groups are trivial a lot of places. So on a dense set of elements in X, we want the isotropic groups to be trivial. This is what we call topological freeness. Right, great. So this is the world of dynamical systems. We have some nice group actions, and like a cornerstone in the theory of C-star algebra somehow is that you have a nice bridge between these group actions and the world of C-star algebra, which is by the cross-product C-star algebra construction. And I'm not gonna tell you exactly how to define the cross-product C-star algebra. I will just tell you some of its nicer properties. So you assume that G acts on X. And for this talk, I will be considering the reduced cross-product C-star algebra. It's not so important what the difference is, but this is the one I consider if you know what these things are. So it's a C-star algebra which is incorporating the information about the group action on the space. So basically you incorporate the topological space by considering the continuous functions on the space. This sits inside the C-star algebra. And then you want to incorporate also the action of the group on the space. And you do this by having this unitary group of G, which satisfies that whenever you take the adjoint of F with such a unitary, you exactly get F composed with the homomorphism. So somehow you have your space, and then you have these unitaries that implement the action, and then this should somehow give you the C-star algebra that comes from the dynamical system, right? There's a few things you will need to know about this cross-product C-star algebra. So first of all, I will probably say this a lot, so I wrote it down to make sure that this was somehow clear, that this copy of the continuous functions inside this cross-product C-star algebra, I call that diagonal throughout. I suppose to some extent you can maybe think of this a little as in Rui's talk now, you had these diagonal elements. This C star algebra, I did not define it for you, but what you probably need to know is that if you take span of elements of this form where you take some function f and you multiply it with some unitary, you actually have a dense star subalgebra of this C star algebra. So normally you will consider this object as being the closure of this span, right? So you have a nice big dense star algebra where you can manipulate these things and you kind of know how this algebraically works because you know how the unitaries work, you know how they commute with these functions on the space. And lastly, also as Rui very quickly mentioned in his setup, we actually have a conditional expectation from this cross product down to this diagonal, which basically kills these FUG if G is not the unit. This is kind of the things you need to know. And then right before I got up here, I realized there's probably one more thing you need to know, because often when you work with C star algebras, you're kind of interested in knowing when they're simple. And the C star algebras I will talk about in this talk will all be simple, because there is a result that says that if your action is topological free and minimal, then the corresponding C star algebra will be simple. And this will be the setup we're working with. So the idea is somehow that you have this cross product C star algebra, very nice setup where you build a C star algebra that kind of remembers things from the dynamical world point of view, right? So. Oh yeah, so I think one way to define it would be that it's so let's say it's from a C star algebra A down to a sub C star algebra B inside of A. Then it's positive, linear, idempotent. How do you say? So P of B should be B for B and B, and then it's a contraction. I think this should be enough to define it. Yeah. I don't know if there's a good intuition about how to think about these conditional expectations. Yeah, I think this follows from this definition, that when you use P again, you get back to the same. Yeah. And actually, yeah. Yeah, so here you can basically just, here the important thing is somehow just that, here the important thing is somehow just that, that the map that throws away all these FUGs where G is not the unit actually is a nice continuous map from this C star algebra down to the small one. It's really the only thing that's yes. P of f is 0. So basically when I say C of x sits inside of the C star algebra, I mean by considering, so UE will be the identity anyway. So you consider C of x inside of here in the sense that you think of FUE somehow in this setup, right? So this is exactly the one it doesn't kill FUE, it will just it does nothing on C of x, so it just gives the identity, right? Okay? That's the conditional expectation. It's not that important, but you need to know that it exists somehow. Any other questions? Perfect. Good, so that's all perfectly nice. Of course, when you're working with KMS states, you also need a one-parameter group or flow. And here we only have a C star algebra. And for this talk, I'm going to focus on a specific kind of one-parameter group, because I'm only really interested in one-parameter group that arises somehow from this dynamical information. So I wasn't sure if I should include the definition of a KMS state. I normally do when I give a talk like this, but I figured exactly in this conference, maybe I didn't have to. So thank you, Rui, for already showing the KMS condition. For me, it was perfect. It was perfect because you didn't assume that the KMS state was invariant for all beta, which is nice because this is also the definition I will use. So it's absolutely perfect. I don't know the KMS condition. I'm not sure if you've never seen it before. It doesn't bring a lot of illumination about what you're actually working with somehow. It's more the kind of thing that, yeah, I'm not sure the first time you see it, it makes a lot of sense. Is what I'm trying to say. Okay, so we're working with some kind of one-parameter groups as well, and we specifically want some that actually comes from this dynamical information that we're working with. So very specifically, I will consider one-parameter groups that comes from something called continuous one-core cycles for the group action. So when you have a group acting on a space, you can, a continuous one-core cycle will be a map from G times X, which satisfies this one-core cycle condition. And specifically, I want this to be continuous as well. Since we're working with C-star algebras, all these things somehow has to be continuous. And why am I interested in these things? Well, they actually give rise to flows or continuous one-parameter groups on the cross product. So if you have an action of a group on X and you have a continuous one-core cycle, then you can sit down and prove that there exists a continuous one-parameter group, which I will denote alpha big omega t, on the cross product. And on these nice elements FUG, it simply acts by multiplying E minus IT omega g on the right. So this E minus IT omega g is just a continuous function, since omega was continuous. So this element here lies in C of x, which lies in the C-star algebra. So it makes perfect sense to multiply it on the right. So somehow you can say that this kind of, this makes perfect sense to consider this kind of one-parameter group from like the dynamical system point of view, because these continuous one-parameter groups exactly arises from the dynamical systems. The question is maybe how much sense does it make from the C-star algebra point of view, but I would say that it makes some sense. Oh, this I should say first. By definition, this one-parameter group fixes everything on the diagonal. So we call these things diagonal, since they fixes the things here. And I'm trying to say is that this also somehow makes sense from the C-star algebraic point of view, because it turns out that when your action is topological free, which all my actions will be, in fact, all one-parameter groups that fixes this diagonal will arrive by these co-cycles. So from the C-star algebraic point of view, the flows we consider are exactly the flows that fixes this diagonal. And it turns out, arises very nicely from these one co-cycles. Good. So the co-cycle condition might look a little weird, so I brought one calculation for you guys. It is, after all, a math conference. Yes? I mean fix point-wise, but actually it turns out, I think if I remember correctly, that if it fixes it globally, it fixes it points-wise. I think one can prove this. So it fixes in any sense somehow. At least in the topological free way. Yeah. I brought one calculation for you guys. So if you have a unitary UG and a unitary UH, and you want, imagine that what I really want in life is for this alpha T omega is to be a star isomorphism, because it should be, right? Which means that when I apply it on UG and then apply it on UH, I should get the same as when I applied on UG-UH. So somehow I want this expression, this is where I apply alpha T omega on UG, times this expression, this is where I applied on UH, to be this expression. But this, what I'm really saying here is that you can actually move this function on the other side. That cause this, by definition of this cross product, that you compose it with the action of H. And then you exactly get the co-cycle condition when you look at these two things. So that's how you can see that this will actually work out when you have this one co-cycle. Okay. So these things will give you your flows on the C-star algebras. Now, if you had, like most of the talks you normally see when you go as a C-star algebra person to this kind of conferences, is people that have like a C-star algebra and some kind of flow, like we had in this last theorem, and then you can somewhat say, what does the beta KMS stage look like for different beta? But somehow my approach to this is a little more general. This setup is very, very general, so for every time you take different omegas, you will give a different size of your beta KMS simplex and everything. So I'm not really going to be interested in investigating each specific beta KMS state. I will be interested in a subtler question somehow, which is just the existence. So instead of saying at this point there is this bigger simplex, I will mostly worry about, does there exist a beta KMS state at this beta? And this is what we call the KMS spectra. So basically, this definition works for any unital C-star algebra and flow. The KMS spectrum is just the set of betas where there exists a beta KMS state on the cross product. So if you took, for example, Rui's last talk, the KMS spectrum would be the interval from the logarithm of n to infinity. That would be where there existed a beta KMS state. And this is really the only thing somehow to some extent that I'm interested in here. And why will show up in a bit. So in this setup, it's the KMS spectrum is just for some one cocycle omega is the set of real numbers where there exists a beta KMS states on the cross product. And general theory tells us that this is a closed subset of the real numbers. If you have a sequence of beta KMS states, you can take some subsequence that converges beta n KMS states, and then the limit will be a beta KMS state. So this has to be a closed subset. And since, if you remember Rui's definition of a KMS state very well, you would have noticed that somehow the zero KMS states were actually just what we call tracial states. So states satisfying that if you take the state on AB, it's the same as taking it on BA. So somehow whether or not these exist has nothing to do with the flow. It just has something to do with the C-star algebra. So what I'm saying is that the zero KMS states, the tracial states, really you cannot, no matter which kind of flow you take, the question of whether they exist or not just have something to do with the properties of the C-star algebra itself. So this is the thing I'm going to investigate for my setup here. And yes. Yeah, that's actually a very, very good question, because I didn't know what to call it. So if you can come up with a better name, yeah. Made up at home definition. Yeah, you could call it the inverse temperature space as well, I suppose. I don't know. Yeah, this is a very good question. I don't think that there's a final answer to that. It's just, as long as we agree on what the definition is, you can call it whichever.
You're not saying that the KMS states are invariant to the dynamics, right?
No, this I'm not assuming. Yeah, so this definition of KMS state, I assume that the zero KMS states are not right. They are for beta non-zero, right? Yeah, but the zero KMS state is a definition question, and here I define them to be not invariant. Yeah. Why did me and Stefan sit down and look specifically at this question, the existence of them? Well, here Klaus actually comes into the picture, because before I started discussing this with Stefan, I wrote a paper with Klaus on the case of the integers. So we kind of already knew what happens in the integer case. So remember that actions of the integers on a compact metric space were in bijective correspondence with the set of homomorphisms on the space. That you just look at what the action is of one, and then this really defines the entire action of the integers. It turns out that the cocycles are also pretty easy to describe. So the continuous cocycles for an action are in bijective correspondence with the continuous functions from the space x into the real numbers, given given simply by this formula. So one can sit down and check that whenever you have such a function, this actually defines a cocycle. And on the other hand, if you have a cocycle, it's really given by its value on 1. And then you can calculate everything else. So to some extent, this kind of observation works for all three groups. Like you only have to know what happens on the generators. When the groups are not free, then it becomes much more complicated because these relations have to be satisfied. But what Klaus and me wrote a paper about was this case of the integers, and what we proved in this paper was that somehow, at least for us, it was very surprising that these KMS spectra, meaning when does there exist a beta KMS state, for the integers, there was actually only 4 possibilities. Either there was only a 0 KMS state, it was the positive half line, it was the negative half line, or it was the real numbers. That was the only 4 ones, and they all 4 appeared. So really, even though the setup is very general, we're talking about all group actions of the integers on all spaces and all cocycles. The existence question is really not complicated. There's only these 4 possibilities. This is assuming nothing, no. So this is just completely general, any group action on any space. Countable group action on second countable complex space. So even though, I mean, we're not really discussing like what does the specific KMS state look like for any value for beta, but somehow the general question of when can they exist was extremely rigid. And this was the motivation for what me and Stefan then started discussing, namely, what is the role of the group of integers here? So if you take another group, G, can it influence the possible KMS spectra for these diagonal one-parameter groups, right? And to some extent, this might sound like the strangest question ever. So I made a strange example to somehow motivate it a little more, which is namely the question of amenability, right? So if you take a countable discrete group G, then it's known that the group G is actually amenable if and only if all cross products for action of G on any compact metric space have a tracial state. So somehow the idea that states on these cross products can say something about the structure of the group is actually not super weird, right? Because amenability is somehow reflected in states on these things as well, right? So I mean, and this is maybe a little weird reformulation, but you can reformulate this by saying that the beta KMS state for the trivial one-parameter group, they're always tracial states, so you can say that G was amenable if and only if the KMS spectrum for the trivial one cocycle, was the real numbers for all compact metric spaces. It's just a little vague, but the point I'm just making here is that this idea of the fact that states in the C-star algebra says something about the group is not very far off somehow. So we sat down and we started investigating these things, and it turns out as the first thing that if you consider this example, the reason why you have this connection really has to do with G-invariant measures on the space X. So both the existence of tracial states and amenability have a lot to do with the existence of these G-invariant measures on the space. And in a similar way, when you study the setup that we're working with, it turns out that there are certain measures that play an important role in the description of these things. So the measures, these measures are the next thing I'm going to talk about. This is what we call conformal measures. And they were already been studied in dynamical system and ergodic theory in a kind of different setup, going back many years ago. I think maybe most influentially by Denker and Ubensky in the early 1990s. So what are these conformal measures? Well, in the setup that we're working with, let me try to explain it by doing a little math as well. So if you have your group acting on a space, and you have your continuous one cocycle omega, and you take say that there exists a beta KMS state for the flow on the cross product, then we can take this KMS state and we can restrict it to the continuous functions on X. And then by Ries's representation theorem, you get a measure on X. And let's call this measure mu omega. Then it turns out by this KMS thing that the state has to satisfy, that mu omega has to satisfy that when you compose it with the homomorphism phi g, it's equivalent with itself with Radon-Nikodym derivative E beta omega g. So whenever you have a KMS state, beta KMS state, you get a measure on the space X satisfying this condition. And it turns out the other way around. If you take a probability measure on X that satisfies this condition, and you then build a natural state corresponding to this thing, so you take the conditional expectation down to Cx and you integrate, you actually do get a beta KMS state for alpha omega on this thing. So the existence of beta KMS states and the existence of these measures are really the same thing. If there exists a beta KMS state, there exists such a measure. If there exists such a measure, there exists a beta KMS state. So studying this problem is the same as studying these measures. And these measures has been studied in dynamical systems quite a lot, with a very big difference. When people work with these things in ergodic theory and dynamical systems, they have no reason to assume that this stuff is continuous. When they're only interested in measurable stuff. Where here, continuity is everything, because we work with C-algebras. Yeah, P is my conditional expectation. Yes, exactly. I'm not saying that there's a bijection between measures and states. I'm just saying if there exists a state, there exists a measure, vice versa. But it's a very good question, and the point of somehow my next slide. So what I'm really, this result somehow is like from a groupoid theoretic point of view, by really going back to work of Sean from his PhD thesis, these kind of things are very well known when you look at them from like a groupoid point of view. So this is more like an interesting background for people who are not experts in groupoids. But the question of whether this thing is a bijection, each KMS states correspond to one measure. Well, in very many cases it is, and I shouldn't say that yet, but it will come. First, let me just also give you a little more math. So somehow, how do you see that this kind of thing appears? Well, remember that when you take your one-parameter group, it's exactly defined like this. So whenever you take your KMS state on some element f, then by definition, and this is really by definition of the cross product C algebra, when you take the adjoint with UG, you exactly get f composed with phi g. So this is just by definition of how these unitaries work. But then by the KMS condition, we can move this UG to the other side. But the price is by applying alpha I beta, right? And alpha I beta in this sense would be E beta times omega of g. And then these two things disappear. And you're exactly left with this condition. And this is once again an element of C of x. So you can really see how the KMS condition forces you to have this kind of relation. Small proof, yeah. And these measures we call conformal measures. This comes from the world of dynamical systems. And as I said, the spectrum of the flow, since these things exist if and only if the beta KMS states exist, it's the same as asking when there exists a beta conformal measure. And now we get to Marcelo's point. So do you always have a bijection? Well, again, these things are like very well known from groupoid theory of this kind of setup. If you assume that all the beta conformal measures are concentrated on points with trivialized Trobi group, then we do have a bijection. Then there is an affine homomorphism between the beta conformal measures on X and the beta KMS states for the flow. And then every beta KMS state is simply given by a measure you compose with a conditional expectation, and you're done. Somehow this is not so important since I'm mostly caring about like the existence of these things. Yeah. So the point is to know these things, we study conformal measures. Okay, and now we're at that point. I have no idea when I'm started. How much time do I have left? Okay, it's a lot of time. Okay. This is really where my discussions with these things started with Stefan. So we asked ourselves the question: what in this result on like this kind of rigidity of existence of KMS states, which role does the group play here? And Stefan was the perfect guy to discuss this with, because for quite some time he'd been doing some very, very influential work on Bernoulli actions of groups. So we had like a really good intuition about how these kind of non-singular measures intuition about how these things behaved. And of course the setup here is different because things has to be continuous. But yeah, he had some really good insights on these things. So the first thing you kind of want to try to do is to just see if this kind of approach from the integers would work more generally. And it turns out that it does. So we were able to prove the following. And this also, Klaus Thomsen plays a role in this thing, because this was somehow, he was involved as well in this stage to some extent. So we were able to prove the following, namely that if you take a finally generated group G of sub-exponential growth with a word length function that we'll denote by numerical G, and you have any action of G on a compact space and any continuous one cocycle and any real number beta, then you can prove, similar to the case of the integers, that there exists a beta conformal measure if and only if there is a point of your space such that this lim sup for G going to infinity is less than or equal to 0. So somehow we could describe completely by the behavior of this omega G if there existed a beta conformal measure or not. And the point of this formula is that if you look at it closely, you'll realize that if this is true for some beta, it's true for all beta of the same sign. I mean, if you multiply this by a positive number, you still have that the lim sup is less than or equal to 0. So somehow the sign of the beta might matter, but the value of the beta does not. Or in other words, if you take a countable group such that every finally generated subgroup has sub-exponential growth, you let it act on a space by homeomorphisms. You take any continuous one cocycle, then as in the case of the integers, you only have 4 possible KMS spectra. You either have a 0 KMS state, you have the positive half-line, you have the negative half-line, or you have the real numbers. So for groups of sub-exponential growth, it's extremely rigid. I mean, if there exists a positive KMS state, they always exist for all positive numbers, and if there exists a negative one, they exist for all negative numbers. Of what? Of the group? Yeah. Yes. I never really looked at the locally compact case, but the thing is, when you go to like the locally compact things, you really want to be studying KMS weights instead of KMS states, because then you have a non-unital C-star algebra. I think my best guess would be that this result is also true in that case, but I didn't actually look at it like this. But I would expect that it would also be true in that case. Yeah, I didn't really consider it too much. Yes. So this is including 0, these two. So the 0 one is always there. Yeah, because the groups of sub-exponential growth are amenable, so they always have a threshold state. Yeah, good question. we saw this, and then I was like, yeah, they're always going to be like this. At least for all amenable groups. I was like, this has to be rigid always. But Stefan, being much wiser than me, was not sure. So we tried to see if there was cases where it was not this rigid, and we came up with a theorem saying that there actually exist amenable groups where this does not happen. And I will just throw the theorem at you, and I will try to explain everything in more detail. But let me just throw it at you at first. So what we proved was that whenever you have a sequence of non-trivial finite groups, and you consider this direct sum group acting on the direct product by translations, then you have a natural action of the Rath product group on this product group x to the z, which is minimal. It's a minimal action. It's uniquely ergodic, meaning that there exists only one gamma invariant measure. It's topologically free, which is exactly what we wanted. So minimal topological free means that the corresponding C-star algebra is simple. And it has the following kind of universality property. Whenever you take a closed subset of the real numbers containing 0, then there is a one cocycle with KMS spectrum K, and with the unique KMS state for all beta and K. So basically we have a C-star algebra here where if your worst first-year student comes and gives you a compact set containing 0, there is one of these nice flows that has exactly that KMS spectrum. And it's a nice simple C-star algebra. So also this group is amenable. This Rath product is an amenable group. And it does not have sub-exponential growth, of course, because then it would have a very trivial KMS spectrum. So the point is, the moral is somehow that even within amenable groups, when you go outside sub-exponential growth, you suddenly can see a crazy variation in what these KMS spectrums can do. So actually, properties of the group are reflected in some sense in this KMS spectrum, right? I mean, somehow these groups, there is some kind of property, I don't know which, but there is some kind of property which are reflected in what can happen with these KMS spectrums of groups. Okay, so let me try to explain a little the setup here. So what do I mean when I say the product action of lambda on x? Well, I simply mean that you take the sequence and you act entry-wise. What is the Rath product? Well, the Rath product is this construction where you can always assume that set acts on this direct sum by shifting the elements. And the Rath product is then this semi-direct product, which is basically this set, where when you define the product, you incorporate the action on n when you compose these two things. And the natural action of the Rath product on x to the z is then that the lambda set part acts on x to the z pointwise as well, and the set part acts on x to the z by shifting. So this turns out to actually define your action. So this is somehow the group acting on the compact space that we're looking for. And I don't want to say anything about the proof. I do want to say one thing though, and that's about these cocycles, because so far I only showed you that cocycles are easy to define for the integers. And I said also if you take any free group on n generators, it's easy to define a cocycle because you only have to know what it does on the generators. But when you take groups that are not like this, you have more relation that has to be satisfied, and then it becomes extremely complicated to actually find interesting one cocycles. So I just wanted to say that in this setup, somehow the reason why we can do this in the setup is because, well, if you have a cocycle on lambda acting on x, then it is actually easy to define a cocycle on lambda set acting on x to the z, because you can define it by summing inverse. So exactly here, when you go from lambda acting on x to lambda set acting on x to the z, it is possible to construct cocycles, a lot of cocycles. And secondly, really the Rath product, if one sat down and checked these things, it turns out that if you have a cocycle for lambda set acting on x to the set, and you have a cocycle for a set acting on x to the set, which is easy to define because that was just by defining it on one, then this actually extends to give you a cocycle on the Rath product. So really, the reason why this theorem works with this kind of group is that you can build cocycles on finite groups, then you extend it to these things, then you extend it to the Rath product. So what I'm trying to say is that there's a reason why the group looks like this. It's because that's the best place to define cocycles. Okay, so what when you go outside the amenable groups? Well, there you can get a similar kind of result. So outside the amenable groups, you do not need to have a zero KMS state. You do not need to have a traceable state. So we could also prove that the free group emits a free and minimal action on a compact space with the other universality property. So whenever you take a compact set that does not contain zero, there is a continuous one cocycle with this KMS spectrum K, and with the unique beta KMS state for all beta and K. So these two C-star algebras can realize every KMS spectrum. One can realize all the KMS spectrum with zero, the other one can realize all KMS spectrum without zero. And the point is that these things actually comes from dynamical systems. And when we did this, there was the first of two such simple C-star algebras that could do these things. But since then, now Klaus is not talking, but he made similar results using heavy classification theory, to get similar results. But this is somehow dynamical version of it. Okay, I think that's all I wanted to say. So I hope I'm okay with time. And thank you for your attention.
So questions or comments?
Yeah, one curiosity is that what is the role of exponential growth in the proof? Does it appear in the limit that you compute?
It appears actually so. It appears actually. So if I show you this theorem, I go back just a second. This theorem. Yeah, no. So this is an if and only if, and we actually need sub-exponential growth in both settings. So when you go one way, you take this point x, and then you I don't remember the exact formula, but you build like you take the direct measures of the orbit, and then you use sub-exponential growth to somehow take a limit, and you really need sub-exponential growth to take this limit.
You have to have a convergence of something along the orbit.
Yeah, exactly. Exactly. And there you need the sub-exponential growth. But interestingly enough, I think we also needed it the other way. So you also needed to say that when you have a beta conformal measure, this point exists. But I don't really remember the details of that proof. But it is really vital.
Orbit, but you can add create a conformal measure by adding over.
Yeah, exactly. You add over the orbit, and you need the group to not grow too big somehow to do this, right? So, yeah. Yes.
In this situation where you have a single point, if you're given one,
yeah.
can you use it to build the others?
No, you cannot. I mean, I should be not so categorical in the sense that, of course, this is a major setup. If you take different cocycles and some of them will just be like this kind of same Gibbs state always, where it's just like they're equivalent to each other somehow. But even in the case of the integers, you can have variations in the type of the KMS state. So like at value 1, it's a type 3 KMS state, and at value something else, it's a type 1 KMS state. So really, you actually have crazy variation in the kind of KMS states. And I mean, they will vary continuously in the week, but you also have differences in the size of the simplexes. So there's not always, in general, if it's unique, it should always vary continuously in the weak topology, I think, yes, because then you then you have a limit thing saying that this should happen. But in general, I mean, I did this for one chemistate, but you can actually take, when you have this result of me and Stefan, you can take another result by Klaus on AF algebras, where he builds, and in one, the chemist spectrum is the real numbers, but for every different beta, you have a different Bauer simplex as the simplex, and then you can add these together, and then you get still the same setup actually. You get this nice co-cycle flow on the cross product, whichever chemist spectrum you want, and at each point, whichever kind of simplex you want. So you can really get the most insane variation in these simplices. Everything can happen, which is why we don't, in this setup, we don't study like specifically what is this chemist state, because simply everything can really, the setup is really big, so there's a lot of variation. Yeah, can't say one thing.
More questions?
What is the lemma? I thought the expression that you took, I'd like to know if the beta of beta really matters or just the sign of it.
It's just the sign. Yeah, it's just the sign. So this is really, so this lemma somehow straightforwardly gives that you only have these four, because if it's true for, say, beta equal to 1, it's true for all positive beta. So that is really just the sign. There's a big difference between the integers and the sub-exponential growth in one point, and that's the fact that Klaus and me proved for the integers, very specifically, that if your action is minimal, you actually only have two chemist spectra, 0 and the reals. But this I've not been able to prove for the sub-exponential growth. So it's still open if you have a minimal action of the sub-exponential growth. If you can actually have only two spectrums, I don't know. That's the case for the integers.
More questions or comments? So let's thank the speaker again. Renault from Université d'Orléans. He will speak about cartel subalgebra in AW star algebras.
Okay, thank you very much, Rodrigo. So first, let me thank the organizers, and especially Rodrigo for being there. It's not my first time in Brazil, but it's my first time in São Paulo. So it's a great experience. And now I'm going to talk about cartel subalgebras in AW star algebras. So although we haven't heard the term cartel subalgebra so far, it has implicitly been present in the two previous talks. I will give the definition of a cartel subalgebra a little later, and I will say a few more things. But first, I'll give a few words of introduction, and here is the plan. So Boolean groupoids and Boolean inverse semigroups, which play, in fact, that will be the key results for obtaining Cartan subalgebras in AW star algebras. And it's also known as non-commutative stone duality. So stone duality is the duality between Boolean algebras and some spaces, and it's extended to groupoids and inverse semigroups. We need, okay, I will say a few words about twists, which is a very important notion when you study Cartan subalgebras. I will say a few things. We already have met partial isometries, and especially partial isometries normalizers. For instance, in the talk of Rui, this unit, these matrix units are partial isometry normalizers. And then I will give the final result. But first, about Cartan subalgebra, I think anybody who studied operator algebras has met the notion of maximal abelian self-adjoint algebra. For instance, if you look at, if you study matrices, and if you do the spectral theory of self-adjoint or normal matrices, then they generate or if the eigenvalues are distinct, they generate, in any case, they always are contained in a maximal algebra. So you got, it's, and I don't know how much, if it's just imagination, but I view these maximal abelian self-adjoint algebras, which are commutative, as a classical window over the quantum world. So at least there is some connection between what we are doing here. That's the classical aspect of the quantum world. And I mentioned, so maximal abelian self-adjoint, that's self-understandable. But if you go beyond finite dimensional C-star algebras, then there are all kinds of maximal abelian self-adjoints. For instance, if you take an infinite dimensional Hilbert space, in the space of all bounded operators, you have basically two kinds of massas. You have the discrete ones, so we have seen you take an orthonormal basis of your Hilbert space and look at an infinity of that, or you realize your Hilbert space as an L2 of a measure space with a non-discrete measure. And then you get another kind of massa. And what distinguishes these two things is this conditional expectation that which appeared in the previous talks. If you have a matrix, you can restrict it to the diagonal. But if you have an operator which is given by a kernel, then of course we would like to restrict the kernel to the diagonal. But it's not a simple process. So the nice massas are those which have this restriction map to the diagonal, which are the conditional expectations that we have met. And I should say a few words, because that's, I was a student at Berkeley at that time, and appeared something that I consider as an important paper, and I still carry it with me in its original form. And you can see that it has been used a lot, but I must say that it's very technical, and it's a result. So what does the result say? Basically, it says that whenever you have a Cartan subalgebra in a von Neumann algebra, then you can realize this algebra as a matrix algebra. You can view the elements as function, okay, on an equivalence relation. So matrices, usual matrices, they are just functions A of ij, of two indices. And if you restrict, you may have an equivalence. These ij, transition ij are not all, they are not all permitted. So you've got an equivalence relation. So it means you have block matrices. So that's the infinite dimensional version of this result. And there is already appearing the word twist. In fact, the basic, as I said, the basic example of a Cartan subalgebra are the diagonal matrices inside an algebra of matrices. But if you want to write matrices, then you need the choice of an orthonormal basis in your Hilbert space. If you only have the algebra which are given, so it's a set of projections, an orthogonal family of projections in your Hilbert space, then you have to pick, if it's maximal, then there will be one dimensional, or if you with a good, and you need to pick vectors in these one-dimensional spaces. And the twist is just appears because of this choice. And so that's, but this will only appear, so as I said, people say, oh, it's an easy result, and people, okay, it's a little technical, but, and it's measure, it's von Neumann algebras, it's measure theory. So it uses a lot of functions of defined almost everywhere, and you have to deal with all this. So I guess maybe 10 years ago, at some thesis defense, I met Professor Takesaki, and he was just aware of what I had done on Cartan subalgebras in C-star algebras, and told me it's the right way to do the Feldman-Moore theorem. Okay, I didn't take it very seriously, but you know, I'm retired and I had time to think of, and that's what I try to do. But I wanted to get a more elementary proof of the Feldman-Moore theorem. But it just happened that it had been done already by these three authors, Danzig, Fuller, and Pitts, and in this paper. But they don't go, okay, and all the ideas are there. But I was not very happy about this paper because they don't mention at all Groupoids. So, and then don't quote my result on, or I say my, it's joint, I would say it's not, it didn't appear as joint work, but Alex Kumjian is also very, has to be quoted for that. But on the other hand, during the last 10 or 15 years, a series of people got interested in non-commutative strong duality. So I quote Mark Lawson, but I should quote Rui and people interested in the theory of inverse semigroups. So, and this makes the connection between inverse semigroups and groupoids. So I'm happy about that. But unfortunately, or not unfortunately, they don't mention at all operator algebras. So I thought on these 2 points I had something to say. So that's what I'm saying here. So first, I just recall what is the classical stone duality. So done by Marshall Stone between 30 and 40 in the 40s. So first, some definitions. Good definitions are very important. And I really insist about these definitions because these objects have kind of many names, and I found this very confusing. Maybe it's a little pretentious to impose my definitions, but I insist. So a Boolean space here is a totally disconnected compact space. So there is a basis of closed open sets. Space is compact. Compact means the Borel-Lebesgue property and Hausdorffness. So that's, and the connection is well known. It's the connection, you realize your Boolean algebra as the Boolean algebra of closed open subset of your compact space X. That's the example. If you go to complete, so complete means the existence of, I call supremum, and they call the lower upper bound, okay, but again, I found this, I will only use the word supremum and infimum in my talk. So arbitrary supremum and infimum exist. So that's, but a complete Boolean space is a compact space which, instead of being totally disconnected, is extremely disconnected. It's a very strange space. It means that the closure of an open set is open. But we met these spaces already. The basic example is the Stone-Chech compactification of the integers. That's, and there is the notion of a measure space, although it's a conference about KMS measures and Gibbs measures and so on. I won't speak at all about measures in my talk. So now, the classical Stone duality gives a one-to-one correspondence between Boolean algebra and Boolean space, which I've mentioned, the way it works. It's from a Boolean algebra, you have to recover the space algebra, which is usually a space of ultra filters on the Booleans. And it extends to complete Boolean algebra and complete Boolean spaces. And the last, in the hierarchy, you also have this duality between measure algebras and measure spaces. I'm not very specific about this last. No, that's classical Stone duality. Now, and for us, it can be viewed as a particular case of Gelfand duality. We know that any commutative C-star algebra is, also, I would say here in my talk, algebras, C-star algebras have a unit, but it's not a problem. But just for the sake of simplicity, my algebras have a unit. Commutative, so usually if you want to deal with locally compact or compact spaces and commutative C-star algebras, there is a notion which replaces the notion of Boolean algebra, which is the notion of local. But I want here, I stick to this particular case. So Boolean spaces and AF means approximately finite dimensional algebras. These are algebras which can be obtained as the closure of an increasing sequence, or in my case, it could be a net of finite dimensional system algebras. Now, in this case, what corresponds to complete Boolean space is commutative AW star algebras. So it's not the term that even that C star algebraists know too well. And so it's a C star algebra which has these two properties. It is generated as a C star algebra by its projections. So, so it has a lot of projections. And second, every orthogonal family of projections has a supremum. That's AW star algebra. And the base, I would say more. I would say more things about AW star algebra in the general framework. They were introduced in the 50s by Kaplansky as abstract version of von Neumann algebras. Of course, von Neumann algebras are AW star algebras, and you can, but they are not every. And we know that commutative von Neumann algebras, at least under severability assumptions, correspond to measure spaces. So that fits the duality. So that's what I wrote here. Now, to get non-commutative strong duality, it's quite easy. And that's something that we like to do, just replace space by a groupoid. That's, and replace Boolean algebra by Boolean inverse semigroup. So I will say, I will give the definition, Rui mentioned inverse semigroups in his talk. I will give in the next slide the definition of an inverse semigroup and a Boolean inverse semigroup. But for Boolean groupoid, and I don't give the definition of a groupoid here. And in fact, I just realized that it hasn't been done. I don't know if I should. Yeah, I don't know if I should do it.
You finished the thesis, but you can continue now.
No, I just have to write my notation. So we have to map. I call it that the domain and the range, and we have. So you can only compose things which match. So the domain of gamma has to be equal. So they go like this, gamma prime, gamma. Is the range of gamma prime. And this maps into, there is a product map which is defined here. And also we have an inverse. And a topological groupoid, you want all these to be continuous. And there is an assumption that we always require that these maps are open, and if there are local homomorphisms, we get what we call an étale groupoid. And all the groupoids which appear will be étale. So the unit space, I'm just assuming that the unit space here is a Boolean space. I must say the basic example of a groupoid is a group acting on a space, and then the semi-direct product, which came in the construction of the cross product that Johannes mentioned, is a basic example of a groupoid, a group acting on a space. So it covers groups, it covers spaces. And complete Boolean groupoid, it suffices to ask, it's just a condition on the unit space. But the definition of a Boolean inverse semigroup is a little more complicated. First, an inverse semigroup, again, okay, now I'm not going to change the terminology. I think it would have been better to call it a pseudogroup. But pseudogroup has different meanings. You speak of a pseudogroup of transformations. And you speak, a group of transformation is a group of transformations. So, but, okay, inverse semigroup, that's the word which is used. So it's a semigroup, so you can multiply two elements, and there exists an inverse. Each element has an inverse in the sense that for any S, there exists a unique T, such as STS equal S and TST equal T. And I denote some S star, sometimes denoted S minus 1. But the two, for me, the basic example, and also a very important property, is that the set of idempotent elements form a commutative semigroup. So with respect to the natural order, it's an inf semilattice, and that plays a big role in the theory. And if you have an element of the semigroup, you can also have the domain, which is S star S and SS star. Those who are familiar with partial isometries know that two partial isometries or two projections, the product of two projections is not in general a projection. It is a projection if they commute. And two partial isometries, the product is a partial isometry if the domain, if you have this commutation relation on the domain and the range. But whenever you have a star semigroup of partial isometries, it is an inverse semigroup with this natural structure. So the idempotents are the projections. Or when I say projections, it's always self-adjoint projections. And the other example we have met in Restoke, the partial bijections of a set, as in Restoke, form an inverse semigroup. And here the inverse is just the natural inverse. So a partial map is just a map defined on a subset onto another subset. And I want it to be a bijection. Now, Boolean, it's a little, the definition, in fact, it has evolved in the time, but I think here, I think it has stabilized. So first, you can define an order of an inverse semigroup, which generalizes the order. It was met with, if you have a semigroup of partial isometries, it's just, you will say that S is larger than T if S is the restriction of T, if you view them as projections on a Hilbert space. So that's the natural order on the set of isometry, partial isometries. So a Boolean inverse semigroup, first you ask that the idempotent form a Boolean algebra, and let me use this. And you ask the existence of a supremum for any orthogonal pair of elements, where you say that S and T are orthogonal if it means ST S star T and T S star S equals 0. So also you say that the range and domain projections are orthogonal. And if you go, instead of 2, you go to an arbitrary family of elements, and you say that the family is a family of idempotents is orthogonal if it satisfies this condition, and an orthogonal family of isometries You want the domain projections and the range projections to be orthogonal families. You want the existence of the suprema. So these are, it appears now as natural definitions. And once you have these notions, then you can state strong duality. But so how do you go from a groupoid to an inverse semigroup? There is a notion of bisection. So say we have these two maps. So a bisection is just a subset on which the domain and the range are one-to-one. That's just. And you say that it's continuous. If then they become homomorphisms on two open subsets. I mean, I said that we are mostly interested in étale groupoid, where D and R are local homomorphisms. But for extensions, I need the notion of continuous bisection. Because so you go from a groupoid, a Boolean groupoid, to a Boolean inverse semigroup by considering the compact continuous bisections. Sometimes this is called the ample inverse semigroup of the groupoid. So it's a natural way for, and of course you go from you see here G0 is we already know that the compact open or clopen subsets on G0 are a Boolean algebra. So in order to go to the inverse semigroup, we just have to consider the bisections. And now to go the other way, okay, there are several ways to go, and Rui, I think maybe he will agree with that because he's one of the first one who introduced this construction. But he also uses another constructions, which are ultrafilters. And here it seems that I don't need to go to tight representations. They are already tight since I have my Boolean algebra. But Rui may. I'm glad to present this talk here in front of some experts. It's not published work, and if I make a big mistake, that won't be, I will probably be corrected. Just as what? In any case, a semigroup acts by conjugation. So if E is a projection or an idempotent, S, E, S star is also an idempotent. So that gives you an action. So if you have an action on the projections, then you get an action on the spectrum. So, and the spectrum of S0 is X. So S acts, so automatically, whenever you have an inverse semigroup, you have an action of this inverse semigroup on this space. And an action of an inverse semigroup is called, as I said, it's a pseudogroup of transformations. So my notations, DS projection here correspond to a compact open subset of X. And so here, automatically, an element S defines a partial homomorphism of the space, automatically. And then, when I have a pseudogroup of transformation like this, I can consider germs. So the elements, I consider triples. So S is an element of S, X is a point in the domain of S, Y is just the image of X by the transformation given by S, and I say that these two elements are equal, or if they are locally, they are equal at X. So I assume the existence of an element E such that X is in the domain of E and SE equal T. That's the germ of S at X. And it has a natural groupoid structure. You just multiply S with T. That gives you the product. And the inverse is what you expect. So you get an étale groupoid. And if S is a Boolean inverse semigroup, then germ S is a Boolean groupoid, the groupoid of germs of S. And I define two constructions. One is taking the bisections and the other one is taking the germs. And in the category of Boolean inverse semigroups and Boolean groupoids, it's just an equivalence of category. It's a one-to-one correspondence between this. So that's non-commutative Sturm duality. So the point is that when you go from, so you want to go from S, you go to the groupoid of germs, and then you have to go back to bisections and to show that you are back to where you started. So the point is that an element of S defines a compact open bisections, obviously this one. And that gives you an isomorphism of S into the bisection of the germ of S. And conversely, given a groupoid, Boolean groupoid G, you take a map of G, an element G, and you consider a triple like this, where U is a compact open bisections containing gamma. It shows that it's well defined, and also you get some of them. So I would say that the proof is very easy, like this, very natural. So I guess that's all about non-commutative Sturm duality. You say I want to reduce the proof of the main theorem, Cartan subalgebra in AW star algebra, to, as we said, to nothing. Once we've got the right definitions, then the proof should be obvious. But we have to do a little. We have a twist to take into account. So a twist. Okay, twist over, and there is something which is called groupoid cohomology and inverse semigroup cohomology. And where you have cocycles. So in fact, we met one cocycle in Johannes' talk. But for two cocycles, it's better, just like with groups, two cocycles are related to extensions, group extensions. But here I'm looking with to cocycles with value in the circle value to the cocycles, and it's better to view them as extensions. Because if you want to look at them as functions, you need sections. And sections we make already, I can avoid to make choices of sections, so I prefer. So it's a notion, I should say, introduced by Alex Kubjan. That's an important notion here. So the object is a groupoid, and I decorate it by a sigma, which is a twist. Sigma, that's what I call a twist. And it has, in the locally compact case, it makes sense too. I'm not assuming that the groupoids are Hausdorff. So here the condition, J is, of course, is an injection, and I always view this as a subset of sigma. But the condition is that in the topological case it should be locally closed. And you can, there are different ways of expressing that. It suffices to look either at this map, which is just groupoid homomorphisms, or you can look at this map because you can recover G as the quotient. You can view this as a normal subgroupoid, and you have the construction. So you have different ways of viewing twists. Now, it took me some time to define the twisted inverse semigroups. What's the corresponding notion? Because you see, here I have something, I have a trivial, this can be viewed as a trivial group bundle of a genome. So what's the corresponding notion for inverse semigroup? And here it is. If I have a space X, okay, I look at its C-star algebra, C of X, and if I look at the Boolean algebra of projections, okay, I have a Boolean algebra, and here I look at the partial isometries. It's something which is not so usual, but a partial isometry is something defined on a Klopen subset, and with it's a continuous function defined on a with value in the circle defined on that. So that's what I call T of X. So a twist is just an extension like that. There are some.
What's T of X?
T of X is just the partial isometries of C of X.
So those are essentially projections with a circle.
Yes, yes, that's true. No.
In T of X.
Inside T of X, yeah. And there are some fancy names. Okay.
Those are functions from X to the circle plus 0.
If you want, you can view them like this if you want to. But I prefer to view them as functions defined on a Klopen subset of X. And it's 0 and 0. Yes. Yes, because I'm on a totally disconnected space. So, and central means that the action, so G by conjugation, and it means that the action here is just the usual action on C of X. That may be the only. No. You say usually I go from Boolean from inverse semigroup to groupoids by taking germs, but I don't want to take germs of continuous of these things. So I prefer, because I will get a bundle. You know, it's étal, but the fibers. I prefer to have as fibers circles rather than germs of continuous functions. But, okay, it's a little subtle point. No, that's not what I want. Okay, so what I do here is just a construction that I've done previously in the paper on cartons of algebra. So that I introduce again. Instead, we have seen that a general germ was given an equivalence class of X, and I had put the Y to make the groupoid structure more apparent. But Y is always the image of X by S. So I only write the first two terms, and the equivalence relation here is a little more subtle than what I had written before, the projections. So I view it. So the difference between G will be a quotient of sigma. The difference is that I don't take the same equivalence relation. Here, I assume that so X belongs both to the domain of A and B, and I have SA equal TB. And here, I assume only that the absolute value AX is here is a complex number of modulus 1. And here I just take the absolute value. So it's just saying that X in the domain of A and B, and I have this relation, and I can invert it, and I am back to the definition that I gave before. So that's the way I extend this non-commutative strong duality to twisted inverse Boolean subgroup and Boolean groupoids. Now, let's go back to, perhaps I should ask how much time do you have left?
10 minutes,
okay, that's fine, yes. So, back to system algebras. So, now I'm interested in usually a commutative subalgebra inside system algebra, commutative system. So, I defined here I'm assuming that I have a lot of projections and I have a lot of partial isometries. So I consider this, okay, it has received several names. In the paper that I mentioned by Thomsen, Fuller and Pitts, they call this object, they call it the groupoid normalizer. I think they borrowed this term from Sorin Popper. But I think a good name would be the pseudogroup normalizer. But sometimes you call, if you have unitaries, you call it the unitary normalizer. So I call it the partial isometry normalizer. I think it's as good a name as. So these are just the partial isometries of A, which normalize B in these conditions. In the previous paper by Alex, when he introduced diagonals in system algebras, and by me, we are considering all elements, and not only partial isometries, but here it will be enough to consider partial isometries. So, really a trivial observation, but which is the key to the result, is that if B is commutative, this subject here is a Boolean inverse semigroup. And its set of idempotents is, oh, maybe I made a mistake here. This is always true. No, I think here I'm assuming that B is maximal. Again, I'm not so sure, but in any case, we know that the projections of B, of course, are inside. Now, the action of, you see, the normalized B. So they define an action on the spectrum X of B. So again, as I did before, I did not phi of u the corresponding action. So I view here du as a compact open subset of X, and same the range, and phi u, it's a homomorphism from du. And one defined the Weil pseudogroup as just the set of these partial homomorphisms. So it's really a pseudogroup of transformations. And we have, if I'm assuming that now that B is maximal self-adjoint in A for any system algebra, then we get a twist. So automatically, whenever you are in this situation of a maximal abelian subalgebra, you get a twisted Boolean inverse semigroup, and from stone duality, not only you get, so you get a twisted Boolean inverse semigroup, and you get a groupoid automatically from the duality. And that, okay, what Pitts, Thomsen, Fuller, Pitts did, they just reconstructed the system algebra from the inverse semigroup. They can't do it, and but it's since I have an étale groupoid, I'm using what I know about groupoid system algebras, so it's easier to reconstruct from the groupoid from an inverse semigroup. It's just a matter of taste. And also note that the groupoid of germs of a pseudogroup of transformation is effective. Or here when I study, it means that the interior of the isotropy is reduced to G0. So it replaces an equiconsolation. It's essentially, there are different words for that. Now, what is an AW star algebra? I gave the definition for commutative star algebra, and you could say that an AW star algebra is a C-star algebra whose maximal abelian self-adjoint algebras are AW star. Or you can the original definition of Kaplanski is every orthogonal family of projections admits a supremum, and every maximal abelian self-adjoint algebra is generated by its projections. So we have seen that the commutative one corresponds to complete Boolean spaces. Now, I said that whenever you have a maximal abelian self-adjoint algebra in the C algebra, you get a Boolean, twisted Boolean inverse semigroup. But if you are inside, if your C-star algebra is an AW star algebra, then the inverse semigroup is complete. Because not only every orthogonal set of projections admit a supremum, but it's also true for every orthogonal set of partial isometries. And an interesting fact here, we spend a lot of time with non-Hausdorff groupoids. But here, an effective, on an extremely disconnected space, an effective groupoid is an equiconsolation. Because, that's strange things with the fixed point of any transformation on an extremely space. Of course, it's closed, but it's also open. So there are equiconsolations. So there are Hausdorff. So here we don't have to worry about that. So it's the principal groupoid is an equiconsolation. It just means an element here is completely determined by its domain in its range. Now, we have to construct the AW star algebra of a groupoid or a twisted groupoid. And the way you do it is just same as you construct the reduced C-star algebra of a groupoid, you use the regular representation. Now, the regular representation is done on a Hilbert space. Here, instead of a Hilbert space, you use a C-star module over over C of X. So it's also called the Kaplanski module. I just learned that C-star modules were introduced by Kaplanski 20 years before Paschke and Riefeld. So quickly, what's the definition of an AW star module according to Kaplanski? That's a C-star module. It's a notion. So you have an inner product, but instead of taking value in the complex numbers, it takes its value in a commutative C-star algebra, C of X. And then it was generalized to non-commutative C-star algebra. But here I'm only interested in the original case. So it has two more properties. So you can, those who are familiar with sheaf theory, is that you can glue in a sheaf. One property that you require on sheaves is to, if you have elements which are defined on a partition, or not exactly on a partition, but you can glue them. And the same, that's the first condition. That's the second condition, that if you have, that's the main condition here. So you have elements which are just defined on Klopen subsets, xi, and you know that the union or the supremum of this Klopen set is everything, then you can reconstruct an element, xi. That's the condition. So now, here the regular, you have a concrete description of the regular AW star module. So here it's its definition. Just look at here. These are section sigma. It's a line. It's a circle bundle. There is a line bundle associated to that, and C of G of sigma are just the continuous sections of this line bundle. So that's the condition. And lambda x is just a counting measure. Here, in the étal case, G is étal. So just the fiber is just a discrete set. So it's a counting measure. I won't say countable because usually it's not countable. And just the usual formula for L2, the regular bundle, make it into a module. And it has a natural CX valued functions. And it is generated by the continuous functions with compact support. The key fact here is that on an extremely disconnected spaces, a lower semi-continuous function is equal to a continuous function up to a meager set. That's, of course, the complement of a meager set is dense, so this continuous function is unique. And this function here is lower semi-continuous. That's now. The regular representation is always just as in the usual case. It's here I choose left convolution on the left. So that's the representation as operators on this module instead of a Hilbert space. That's the regular representation. And that's no problem, that's well defined. That's a nice thing about if they are bounded, they are automatically adjointable because it's an AW star or W star module. It is self-adjoint. So it's automatic. But that was observed by Kaplansky in his early papers. Yeah. So. And you look at the AW star algebra generated by, I didn't say, but the bounded operators, this algebra that are here, is an AW star algebra. So you look at the AW star subalgebra generated like this. Now I come to definition of a carton. So I said, Mazars, we have seen. Conditional expectation, okay, I don't have to give again the definition, and I want it to be faithful, so P of A star A equals 0 implies A equals 0, and I want it to be completely additive on projections. But then note that if you take P of a sum of projections, you get sum of P, the P's, but the image of a projection is not necessarily a projection, but it's a positive element. And AW star, commutative AW star algebras are what's called monotone complete. But I prefer to stay in the realm of AW star algebra rather than monotone complete algebra. And here there is something which bothers me, and so I make the natural assumption that the normalizer generates A as an AW star algebra. That's the natural assumptions. I need also this condition. So if this is equal, so if the scalar, the inner product of A with U with any U in pin base is equal to 0, A has to be equal to 0. I cannot prove, in the von Neumann algebra case, 3 implies 4, and I'm not able. But I think it's just because I don't know enough.
Condition 2, we're talking about the orthogonal family of projections
Yes.
and the supremum.
Yes.
So you say the P of the supremum should be the sum.
Yes, you say you can sum. It's a supremum. Yes.
The supremum on the positive.
Yes. Yeah. And here is the theorem. So first, if we start with a twisted principal complete Boolean algebra, then we get the unit, the continuous function of the unit space of G is a Cartan subalgebra. And the converse is also true, Cartan subalgebra. Then the Weil twist, I said that it's a very natural, it's a twisted principal complete Boolean algebra. That's pretty easy. And then there is an isomorphism of A onto the AW star algebra of the Weil twist, carrying B onto C null of G null. And we have an explicit expression for it. So it means we just realize elements as matrices, as you can see. So I can view them, an element A, I can view it as a matrix of a GOB. So I have an explicit expression. And just a word about the proofs. The first part, we do things at the level of compactly supported functions, but all the work was done. I had done all the work in the paper on Cartan subalgebra and C-star algebra. It's exactly the same. And here, a result of Widom. Widom was a student of Kaplansky. He worked on that before doing great other things. And the GNS representations is an isomorphism AW onto an AW star algebra, subalgebra, which is here. So looking at A, or looking at its image in the regular representation, so on the GNS representation, is the same. So I will look at this rather than A. And
you're calling this a GNS representation, but it's more like a dilation.
Yes, but in the paper, Widom just say that it's a natural extension of the GNS representation. You just complete A with respect, you have the condition. That's the role of the expectation, to be able to define the regular. And you put all this together, and because here this isomorphism respects the expectations, so you construct. You see that these two things really match. So the image of A, you identify the modules with this. You have a unitary isomorphism. So identify the module constructed from the expectation with the regular module, which is here, and you have this. This map, in fact, is implemented by the unitary, and once you have this relation, then it's clear that the two you get isomorphisms of these two AW star algebra, which does the right things. Okay, I didn't too brief, but I don't want to. So that's.
Questions or comments? Oui?
Do you claim you get Feldman rules from this?
There is no, I don't. There is a work, there is the last part which has to be done is to analyze measures and to go back to reality, because these spaces X extremely, I don't want to stick with them. For instance, the main first example to look at is L infinity of n into B of L2 n. You don't want to stay with the Stone-Church compactification, but you have an identification between functions on I and functions on the compact identifications. So here it's a little more complicated because I have to view this identification between some measure space, let's say omega mu. So, when I realize L infinity of omega mu, but you see here I have all the ingredients because I know that my elements of my algebra are continuous functions on the groupoid. So I know what the measure would be, but there is some work to be done. That will be the end of the project. It's not done, of course, by Danzig, Fuller and Pitts.
Also furthermore, the normalizers are unified.
Yes, but it's easy to show that even in my case here, you get the same thing.
Okay. But you could replace your definition of the normalizer
by unitaries. Yes, so in an AW star algebra, it's possible. For an arbitrary C-star algebra, it would be wrong.
Any more question or comment? No? So let's thank speaker again. Two quick advertisements. We will finish today in the coffee break of the afternoon. Probably we will take the official picture after the last talk. So we go to the coffee break and go there and take a picture. Well, almost everybody's here. And Good afternoon. We have more 2 talks this afternoon. Don't forget that after the second talk, go with the Rosaria and confirm if you will go in the dinner or not on Wednesday, okay? So the next speaker is Rodrigo Frausino from University of Wollongong, and he will speak about a construction of topological graphs via KMS states.
Thank you very much, Rodrigo. And I think I should start talking a bit about my background. I was actually, my undergrad was in physics right here in the University of São Paulo. And then I went to do a master in mathematics with Professor Bissacco. Basically because, I don't know, physics was not the kind of stuff that I was super into. I don't know, it felt much like you have to do a lot of programming. I might as well do mathematics, I guess. So, and after that, after my master's degree with Rodrigo Bissacco, I went to do my PhD with Professor Aidan Sims back in Australia, in the University of Wollongong. And that, this joint work with Aidan and Abraham NG, is that what I'm going to talk about today. So, let's start. I will start, don't worry about all these names, I'm going to define everything here, but it is important, I just want to give a brief, what kind of result that I'm going to talk about, right? So this talk is mostly based on a paper called Reconstruction Topological Graphs in the Hilbert modules by me, Abraham Ng, and Adam Sims. And then actually I got the referee report yesterday, and it's being accepted with some. And he just push. So it's a nice thing. Yes. And yeah, so I'm super happy, honestly. So it's kind of crazy. So it's been a super incredible week, honestly. And so don't worry about all the definitions that I'm listing here. I'm going to talk all about them, but just for those that are more, let's say, experts on the field, I'm going to just briefly talk about that. So if you have 2 compact topological graphs, you can then find something called the Toplitz algebra of these graphs. And in this Toplitz algebra, you have something called the gauge action and the coefficient algebra of these graphs. What I'm going to prove is basically, in this talk, is this direction here, which if you have some kind of isomorphism between the triples of these, the Toplitz algebra, the gauge action, and the coefficient algebra, we can kind of reconstruct something called the graph modules of the topological graphs. I'm going to talk all about that today. And more than that, you can kind of reconstruct locally the graphs as well. And of course, the proof is via KMS states. That's why it is related with quantum statistical mechanics, right? So, so let's start. So, like I said, the kind of result that I'm talking about is like if you have an object and a structure associated with this object, if you have an isomorphism between these 2 structures, what can I say about X and Y? That's the kind of very general kind of question that I'm trying to talk about. So there's plenty of examples. I gave some examples from the C-star algebraic world. For example, if you have 2 C0 of X, which is the continuous functions that vanish in infinity, of a locally compact house of space. If they are isomorphic as C-star algebras, we can say that the spaces are homeomorphic. That's called, some people call the Gelfand duality. And something a little bit more difficult, I guess. If I have the C-star algebra, reduced C-star algebra, I have a groupoid. There's some, let's say, more hypotheses as well in the groupoids. And you have these C0 of the unit space as well. If they are isomorphic in a certain way, then the groupoids are isomorphic as well. This is actually a corollary from a result from Jean Renault. Actually, this is something called a Cartan pair, and he proves it more generally with a twist, but in this case it's a trivial twist, let's say. It's just some examples. So today we had already all the definition about KMS states, I guess. So I don't know. I'm just going to talk a little briefly what the definition is. So A and tau is a C-star dynamical system. If A is a C-star algebra, it could be unit or not. And tau is a strongly continuous one parameter group of star automorphism of the star A. It's what we talked about today. And an element of the C-star algebra is called analytic or entire analytic. If there exists an analytic function such that it kind of extends the dynamic of the extends to the whole complex plane of the dynamic of the element A. So that's called an analytic element. And from the analytic element, you can say that phi is a state, is a K-mass state for a parameter beta. If it satisfies this kind of twisted threshold condition, so phi A tau I beta of B goes to phi beta of A. Everything talked in Ruiz talk, right? And Christensen as well. So another definition is called K-mass infinity states, which is basically just taking the K-mass states and, well, putting beta to the beta to infinity. So if you are going to call a K-mass infinity state, if there is an increasing sequence beta n going to infinity, and K-mass beta n states such that phi n converge weakly to phi. And another definition is called the ground states, which is if A, B are analytic elements and the entire analytic function is defined like this. It needs to be uniformly bounded on the upper half plane. Then these guys are kind of the ground state. And using some results from Bratelli's books, we can prove that all the K-mass infinity states are ground states, but the other way around is not usually the case. In fact, the set of all K-mass infinity states are actually very badly behaved. So very different from the ground state set. So something that I saw that Renault talk a little bit about is those modules. I'm going to give the definition of the stuff. So a Hilbert module, a right Hilbert module, is a module of a C-star algebra A. It needs to be equipped with an inner product, but now the inner product is not in the complex numbers anymore. It is basically in C-star algebra. It needs to be C-linear in the second variable. And it needs to satisfy what do you expect from an inner product, right? It needs to be positive. This positive is positive in the sense of C-star algebra, right? And it needs to be positive definite. If it's 0, then x equal to 0. It needs to be linear, right? It goes here. When you change here, you put an adjoint. Exactly right, like the Hilbert space. But now the Hilbert space is not anymore on C. It's in a C-star algebra A. And it needs to be complete on the norm defined by this inner product. Exactly like a Hilbert space. So something that we're going to call a C-star correspondence is, or Hilbert bimodule, these two names that we can give it, over A is a right Hilbert A module together with a star homomorphism between the A and L of X. I just want to say the L of X here. Is the adjoint one. Operators on X. So a remark is that L of X with the operator norm is a C-star algebra. So I should use the white. Okay, sorry. Can you guys read it? So it's called the adjoint operators. And the adjoint operators are those operators T. T is in L of X. You can live. There exists S from X. It's adjointable, right? X. Yeah, it is not obvious. Yeah, it's not always true. There are examples of operators that are bounded, but it's not adjointable. There's no adjoint. That's one of the biggest difference between the Hilbert space and the Hilbert module, basically. So we're X and Y and X. So, and the thing is, this phi basically defines left action. That's why it's called a Hilbert bimodule. The right, and you have a left action as well. So, an example, every C-star algebra is a Hilbert module over itself. When you define the inner product just being the multiplication with a joint on the left side there, the right action is the right multiplication, while the left action is just the multiplication from the left. This is the kind of the trivial Hilbert module. So another definition that we need is something called the topless representation. So let A be a C-star algebra, and let X be a C-star correspondence that I just defined before. A topless representation of X in a C-star algebra B is a pair psi and pi, such that psi goes from the C-star correspondence to B, needs to be a linear map, and pi needs to be a star homomorphism between the C-star A and B, such that satisfies all these three conditions here. So first one is basically kind of a, how can I say, compatibility condition between of the modular structure, let's say. So the first one is kind of linear. You have this, when you start, then this one. It goes with the inner product, and it's with linear on the left side as well. So an example, when you take X to be a C-star algebra A, the module as a C-star algebra, then every star homomorphism is a topless representation. So this kind of notion, in a sense, generalize the notion of star homomorphism between two C-star algebra. And why we care about that, I don't know if, I'm going to just kind of say that. There's something called the topless algebra, a classical topless algebra, and this is kind of related with that. So from the topless representation, we can define something called the topless algebra. So there exists a topless representation. I'm writing as iota x and iota a of x in a C-star algebra tau of x that is universal over all these representations. And being universal, which means that any topless representation psi and pi from X to another C-star algebra B, there exists a homomorphism psi times p pi, such that it goes from the C-star algebra tau of X going to B, such that it kind of satisfies this, makes this diagram commute. So just so we don't need to come back to this slide, I think I'm just to copy somewhere here. So X and D. But of course, it's a very, I don't know, very abstract way to define it. There's a more concrete way to define it, and I'm going to talk about this right now. So a more concrete way to define this algebra is that if you have a C-star correspondence, you can define something called the inner product, the tensor product, and the tensor product is going to be a C-star correspondence as well, with the left action, the right, with this left action, which is basically just, if you get an elementary tensor, it's going to be just the first component. And the right action is the same thing, but on the right. So from this tensor product, we can define something called the Fock space. So people who know quantum mechanics, there's something called the Fock space. So it's going to be the direct sum of all these tensor products. It's going to be, again, a C-star correspondence. And on this Fock space, we can define something called the creation operator. So for every psi in the C-star correspondence, we can define this operator here that goes in each tensor product. It goes from one tensor product to the n plus 1, which is just tensoring the vector here, right? So from these, we can define a matrix. So we define it in the Fock space itself. So we can use this matrix to define an operator T infinity of psi. And same thing for phi infinity of A. And the thing is, I tell you, well, I don't have space anymore. I just wanted to say that the complex algebra is equal to the C-star algebra generated by this infinity with the phi infinity. That is in X. A is algebra. And every guy here is inside the adjoint operators on the Fock space. So what I'm saying is that you can realize the Toplitz algebra inside the adjoint operators on the Fock space. So it's a more concrete way because it's actually operators inside a C-star algebra. Now the thing is, in the Toplitz algebra, we can define a strongly continuous action of the circle T to the automorphism group of tau of X such that, because as I said, the Toplitz algebra is generated by these guys, so you can define it on the generators. So on these generators here, which is Yoda A is the same thing as this guy, right? So on these generators, they are fixed, while on these generators here, you just multiply by Z. So this is called the gauge action. And of course, the important thing that we can define from this guy, alpha T to V, gamma of V to IT, and this is going to be our dynamic. So this one is the one parameter group that we define the KMS states in. So when I write a triple like that, it's going to be A is a C-star algebra, T is the Toplitz algebra of the C-star correspondence, and MA is like these guys here, basically. So in a way, it's looking the C-star algebra inside the Toplitz algebra, so by the map I or A, so phi infinity. So this is the triple that we are kind of interested in. So a definition here, we're going to call it isomorphism of triples. If theta is a isomorphism of C-star algebra tau X in tau V, if it's an isomorphism algebra such that it entwines the gauge action, so kind of commutes of the gauge action. for every z in the circle, and it carries MA to MB, which means theta MA goes to MB, and we denote it by this, like this triple is isomorphic if it satisfies all this. So now, what is a topological graph? So a topological graph is a quadruple, E0, E1, R, and S, where E0 is the vertex space, E1 is the edge space. They need to be locally compact house of spaces. R is a continuous function from the edge into the vertices, and S is a function from the edges to the vertex, but it needs to be a local homomorphism as well, not only continuous function. And for this work, we are supposing that E0 and E1 is compact, and it's called a compact topological graph in this case. So we want to define a toplet algebra associated with this topological graph, and we need to do this construction that I just explained. So the continuous function on the edge is a C-star correspondence over C of E0, which is a C-star algebra, with right action defined like this. Xi times A needs to be xi of E times A of the source map of E. And you need to define an inner product as well on the continuous function on the vertex, which is just kind of this sum here. It's kind of like the standard inner product on the on C of n, but it is it depends on the vertex you are. And so all this kind of what this module is saying is that we are given some information about the source map, right? And we need the left action to say about the right to the range. So the left action is the same thing as the right one, but we change the S to R. So this is the graph correspondence, and we use X of E to be this continuous function on the edges. In the case of compact topological graphs, you don't need to complete it all. Yes, these are ready. Yes, I'm supposing not any one are compact, but it is usually is a it's a pre-Hilbert module. So, but it's really good. You need to complete it in general, but in this case now. So the toplet algebra for topological graph E is then we're going to use this notation. It's just going to be the toplet algebra of this graph correspondence. So there are some examples. If E is a finite graph, finite directed graphs, then the TC star of E is equivalent with the using topless conjugate families for the people that know this stuff. And okay, this is the classical example for finite direct graphs. So some notation that I'm going to use when I put E of 2n is the set of paths of length n. E star is all the paths of finite length, so you know n to n equals 0 to infinity of E to n. And I'm going to put En, if I put a V right beside the E of n, I mean all the paths of length n with the source equals to V. So I just want to point out that the convention that I'm using is like from the right to the left, just like for composition of functions. Some people, like Alex Kumjan, they go from the left to the right. So I just want to point out this. So, and same thing for E star of E. Are those paths there? So the source is V. So now we can understand what kind of the result that I'm going to talk about. If E and F are compact topological graphs, TC star of E and TC star of F are the topological algebra of these graphs. You can define the gauge action that I talked about. MF the coefficient algebras, which is these guys inside the star algebra, right? And if you have an isomorphism of the triples that I talked about, what can I say about the guys that came from there? What can I say about the E and F? What can I say about X of V and X of F? X of V is the graph correspondence. This guy? the graph is C of U1 without the modulo extractor, right? C of U1. So in the case of topological graphs, you can even, I gave this definition of Toplot's algebra, but in the case of topological graphs, you can make it even more, let's say, concrete. You can make it inside a very concrete bound operators on the Hilbert space. In this case, is if E is a topological graph, fix V is a vertex, and let E of mu in the all paths with source V, and we can define these guys define a canonical basis on L2 of E star of V. E star of V is just the indexes, right? It's a Hilbert space. Then there exists a linear map psi of V from the graph of V, graph module C of V1, remember, into the boundary operators on the L2 of E star of V, and a star homomorphism pi of V from C0, but don't need C0 because it's compact, right? So C of V naught going to the boundary operators on L2 of E star of V, such that on the canonical basis of the L2 of E star of V, it satisfies this. So what is you're summing over all the paths whose source is equal to the range of mu, and this is like a diagonal operator where you have this like weight in each one of the bases on the canonical basis. So the thing is, as I wrote here, this is a Topless representation. So from this Topless representation, you can find this map psi of pi of V from the Topless algebra to a star algebra B. In this case, B is BL2 of E star V, right? Which is a star algebra. And the thing is, when you take the direct sum of all these guys, it is faithful. So what I'm saying is that you can view, even in the case of topological graphs, you can view T of X to be something inside the boundary operators of L2 of V star. So in the case of topological graphs, X of V. And we are going to use these maps, psi of V and pi of V. So for a compact topological graph E, the following limit exists. So rho of A of V, this limit entering infinity of max of V on E naught, of En V 1 over N. It needs to be less than infinity. I just want to point out that when E is a finite graph, then AE is the incidence matrix of the graph, and the row of this row of A of V is the let's say is the spectrum radius of this matrix. That's why this notation, I'm using this notation. So for each A in the Topless algebra, for each beta bigger than the log of this spectral radius of this limit, then we can define for each V on the vertex space a K-mesh state. It's very explicit. The K-mesh state is the sum over all the paths whose source is V, E2 minus beta. The module of mu is the length of mu, and we use as well this we need to use the star homomorphism as well, and E mu is the canonical basis of the star, L2 of the star. And this n is basically just a normalization constant. And we can prove that this guy explicit like this, they are K-mesh states, and more than that, they are extremal K-mesh states for the star algebra, the Topless algebra. So a result by Hawkins, it's reading his PhD thesis, if E is a compact topological graph and fix beta bigger than the log of the expected radius, then there exists a fine isomorphism between the probability measures on the vertex space onto the set of Kms states, such that it takes a measure omega to a state defined like this. So it's the integral over all the Kms states here, like over the measure mu omega. So this theorem already says basically that if you have a Kms state in the Thomsen algebra, then you can decompose using this integral basically. So and phi beta of V, they are extremal Kms states in particular. So another thing is that for HV and E naught, we can define a vector state phi V on the Thomsen algebra. Define it like this, it's just these guys. So basically, it's just this. Phi V is just the part, psi V times phi V of A of EV. And we denote by S infinity the set of these states. I just want to say that when you take beta to infinity here, everything is going to cut out but these guys. So what happens is that the weak start limit of these states are going to be exactly these phi V's here. So in the end, what it's saying is that these phi V are Kms infinity states that I talked about earlier. So a proposition that it's something that I was like, don't know, playing a little bit during the thesis, and I'm not sure if it is an original result, so I need to look in the literature, but something that I proved is that if E is a compact topological graph, the set of ground states of the Thomsen algebra, it is equal to the Kms infinity states, which is not obvious because sometimes the ground states are bigger than the Kms infinity states. So I'm not sure if it's yet if it is original work, but something that I proved using these states right here. So the idea is to prove that these S infinity are extremal ground states, and using basically some analysis and showing that it is all they are basically all the Kms infinity states as well. So now I can talk about the actual theorem. It shows up in our work with Aidan and Abe. If you have E and F are compact topological graphs, you have the gauge action, you have the Thomsen algebra, you have the coefficient algebra, which is just the continuous function on the vector inside the Thomsen algebra. So if you have an isomorphism of triples that I talked about earlier, you can like restrict this isomorphism into the coefficient algebra. So what we can do is find isomorphism between the XE and XF. So what this theorem says basically is that from the isomorphism of triples, we can reconstruct the graph modules. So, and it satisfies this thing here. Of course, I didn't talk about what these P of F are, and they are very important for the proof of this theorem. I'm going to talk about them. It is basic projections inside the Thomsen algebra, which I'm going to talk about there. So this lemma here is basically, in our proof, it's basically the only point that the Kms states shows up in the proof, basically. It is this lemma. So if E is the compact topological graph, for each state phi on the Thomsen algebra, we can denote pi of phi, the Johannes representation of the state. And the thing is, you can prove that there exists a unique element, P of V, it is a projection, such that for every guy on S infinity, the states that I talked about earlier, such that it satisfies these two conditions here. So using the Johannes representation, these guys are going to be minimal projections. It's more than that, it's rank 1 projections on the Johannes space. And the states are normalized as well on these projections. So why this lemma is very important is that I want to remember the Kms states, they are invariant for the kind of isomorphism that we talk about. It's like a dynamical invariant. So what this is saying as well, that we can reconstruct the projection P of V from the K-mass states. That's basically what this lemma is talking about. So what this P of V actually is. We can define it in a more concrete way as well. So if E1 is the edge space, it's a compact set, we can cover it, a finite cover of X sections. X sections is open maps, open sets such that the source map is a homomorphism. We can do that because S is a local homomorphism. So we can find a partition of unity, subordinate of two UI, such that xi of I, they are continuous functions, and they're positive. And we can define the P of V to be 1 minus this sum using the Yori axis. Yori axis is the creation operators, right? And of course, it's important to say that the Toeplitz algebra of a compact topological graph, it is unital, so there exists a unit 1. So if you put that in the picture of a Fock space, this P of V is basically going to be the projection onto the first coordinate of the Fock space, the zeroth coordinate.
Would this be the Jones index of the condition expectation?
Could be, right? I'm not sure. But yeah, but that's the curious thing. In the case of topological graphs, the P of V, this projection is inside the Toeplitz algebra, and we need that. And the previous lemma says that we can reconstruct from the K-mass states. That's the heart of the proof, basically. So another definition that I need is the first spectral subspace of a Toeplitz algebra. It's just those elements of the Toeplitz algebra such that when you put the gauge action, it's going to be just multiplied by Z. So these other lemmas, the other very important lemma for the proof of the main theorem. So if E is a compact topological graph, M is the coefficient algebra. If rho of V goes from M to M times P of V is a isomorphism, just multiplication by the projection, we can define the psi of E going from the graph module to the Toeplitz algebra like this. It's basically just T of infinity, but you times the projection. And we can prove that the image of this map is going to be the first spectral subspace times P of V. Remember that this guy here is inside the Toeplitz algebra. We can define in this subspace in a product just like this. So it's going to be the multiplication with the adjoint here, and we go back with the isomorphism rho of V. So this is going to be a inner product inside here. And the important thing is that the graph module and this guy are isomorphic. So what this lemma is basically saying is that in the Toeplitz algebra, we can view the graph module inside the Toeplitz algebra. It's going to be exactly this guy here. No, not necessary. Not necessary. Not the coefficient algebra, no. No. It is a member of the Toeplitz algebra, though. Yeah. In this case. Yeah.
Because otherwise, rho of V will not be an algebra.
It is exactly because it commutes with them. Exactly because of this, yeah.
The Jones index is the central element.
That's true. Yeah, but it isn't. It's important. What we said is that this is almost exactly because the projection commutes with the coefficient algebra. That is true. That's true. So the main theorem is what? If you have a triple that is isomorphic, then which implies the graph modular isomorphic as well. And the proof is basically the two previous lemmas. So if theta is this isomorphism here, we can view these subspaces here. We can restrict And the fact that P of E is reconstructed from the gamma states, we can say that this theta map exactly this space into this. And the previous lemma said that these guys are isomorphic to this, so basically we can find isomorphism between the graph modules as well. So from these two lemmas, you can find, we can prove the theorem 13. So from the triple, we can find isomorphism between the graph modules. We can reconstruct the modules from them, from this kind of data. Another thing, can we do more than that? Like, we have the isomorphism between the graph modules, but can we do more than that? We want to talk about the actual graphs, maybe. So, if E and F is a topological graph, we say that E and F are locally isomorphic. I mean, I want to point out that I was writing this the paper, we defined this thing, but actually it is work by Davids and Rodrigo. We found actually 2 weeks ago, and I would like to thank to Adam Doron and anonymous referee as well that talked about this. That Davids and Rodrigo, they defined this locally conjugate thing, which is exactly what we called locally isomorphic. And you write E log F if there exists a homomorphism between the edges, between the vertices, such that for every V and E naught, there is a neighborhood U on V, such that for each neighborhood, you can find this map, which is associated with U, that goes from the edges, whose source is U, going to the other guy, basically to make it compatible, such that these guys work very well with the range and the source as well. So this is kind of what we are going to call it locally conjugate graphs, topological graphs. So a result by Davids and Rodrigo, it doesn't matter what this tau is. It's something called the tensor algebra, but it doesn't matter what it is. But they prove that to compare topological graphs, if the tensor algebras are isomorphic, then the graphs itself are locally isomorphic, locally conjugate. And in particular, if the graph modules are isomorphic, then the tensor algebra is isomorphic as well, then it comes as a corollary of Davids and Rodrigo 2011 that E and F are locally isomorphic, locally conjugate. It's basically these guys here. It is a non-self-adjoint algebra, right? So it basically is the span of closure span of these guys here, right? So as a corollary, if E and F are compact topological graphs that are totally disconnected, then this isomorphism actually becomes isomorphism of topological graphs as well. So in particular case, when E and F are finite directed graphs, then we can have isomorphism between the graphs as well, because in the finite case, they are totally disconnected. So let me see. Do we have some time, or because I did more than that? Yeah, I have some partial results, but I don't know if we have time to talk about that. So 10 minutes. Unlikely, and honestly, if you guys are lost now, it's going to be worse because my idea was to generalize this stuff for modern topology, compact topological graphs. Because I noticed that what we need is that projection, but it doesn't need to be on the Toeplitz algebra. It can be in the multiply algebra. And that's what I try to do in these partial results that I'm working right now, basically. So, and I need to use some very not usual stuff. So, I don't know, 5 minutes. I think it's better, right? Okay. Because if we go this way, I need to talk about something called upper semi-continuous field or Hilbert space, and maybe it's not a good idea to talk about that right now. Yeah. So let's go to the overview, right? So in the end, what do we have? If E and F are isomorphic, this is canonically true, the triple are isomorphic. We prove in this paper with Aidan and Abraham, we prove that this direction, the graphs are isomorphic. The other direction is canonically true as well, because of the definition of the Topless algebra. David and Roydor proved this direction, but we proved as well in our paper in a more elementary way, but it's important to say that the results are from them. It's a corollary of their work. And of course, there are some things that we can talk about. This direction has a converse, it does not. In our paper, we give a counterexample why this direction does not work, and this other direction is a little bit more complicated. Davidson and Roydor, they proved that when the vertex space has covered dimension 1, then this direction has a converse. But in general, there's some homological, let's say, homological conditions. There's an obstruction for this direction that we kind of talk about in our paper as well. So, but I'm not going to talk about it because it's going to be a little complicated to talk about homology on system algebra here. So I think that's it. Thank you.
Questions?
I have maybe a comment. If I understand it right, in the case of a compact topological graph, XE is a generalized finite dimensional module in the sense that the identity operator is a generalized compact operator.
Finite dimension means it's finitely generated.
More than that. The identity operator is the identity operator on XE a generalized compact operator.
It is a if it is everybody's a compact operator.
Yes, exactly. And
So,
I think it is. And I think that's the main.
I'm not sure if it's everybody's a generalized compact operator, honestly. It is.
I think it is.
Mm.
And in that case, in the condition expectation that your condition expectation is finite Waterton index, and the index is exactly PE. So the comment is that probably you could generalize all of your results for a Topless what's it called?
Topless Kunstkrieger, Pisner, Kunstpinner algebra.
Yeah, just a Kunstpinner.
Yeah,
If your correspondence, if you have an abstract correspondence which is finite dimensional in that sense, that the identity is compact, then I think you have all of the ingredients for your proof. You have a gauge action, you have your PE and everything else, and it would make perfect sense to show that if the two algebras are isomorphic from the point of view of the triple, right? Preserving the
It carries the coefficient algebra.
It seems like your proof proves that the modules are compatible.
Could be.
That might be a direction to generalize it.
Could be. But in the case that every algebra operator is a compact operator, right?
Yes.
Okay.
The first thing would be to check that.
Mm-hmm.
And I think that your formula for the PE is giving precisely the description of the identity operator as a just a guess.
That makes sense to me. Yeah. I can look into it.
More comments or questions? No. So let's thank for the acceptance and for the talk.
Thank you very much.
So 5 minutes break.